Oh no, I haven't let anybody in. There's a bunch of people waiting in the waiting room.
Yeah, no, I mean, but people I think are mistaking signing up to the conference as signing up to Zoom.
Oh.
So they're like, I put my email address and password in and I can't get in. So I'm replying to them and saying, no, you don't have to put that in for the.
I see.
That's not a requirement.
Oh no, I haven't let anybody in.
Sign up for Zoom.
There's a bunch of people waiting in the waiting room.
Yeah, no, I mean, but people I think are mistaking signing up to the conference. Okay, I can see that.
Hi, Jeff. How are you?
Hey, Emmanuel. How's it going?
Right. Yeah. Good.
Very good.
Yeah. How about you?
Let me see. You're the first session chair, right?
That's
Okay,
right.
so let me make you co-host,
Yeah.
and I need to find Nathan and make him co-host. Okay. So I am host, and Nathan is co-host, and you will be co-host. And as soon as the speakers join, we'll let me see if I can find him.
Hey, Jeff, I'm here. This is Shuhan.
Ah, Shahang.
Hey, good to see you.
Yeah, you too.
How are you?
Been a while. Okay, let's see. Okay, Shahang, I'm making you co-host as well for the duration of your talk.
Okay, great. Thank you.
And then we will revoke your powers after your talk is finished.
All right.
Okay, so I'm just, we're live streaming, so that's working out. Okay, very good. So Shahang, let me see if you want to share your screen and just check that it's working, and
Yes,
then
let's try that.
I will have to share mine a little bit, and then.
So should I share the whole screen just to test it?
Yeah, if you just share screen and see that your slides are appearing.
Okay, let me do that. All right. Actually, give me 1 second. All right.
Oh, great. Good. Yes.
Okay, and you see the whole screen, not the presenter's view, right?
I can see the whole screen, not the presenter's view. That's right.
Great, great. Okay, and I guess turning pages works fine.
Works great.
Okay. All right. So I'll stop it now, just not to spoil the fun.
Great. So I think we're pretty much all set. I'm going to start and just make a few announcements, maybe about 10 minutes before, and then I'll introduce Emmanuel, who will introduce you, and we'll go from there.
Okay, sounds great. Thanks.
Okay, great. Shuang, have you been in Taiwan the whole time?
No, I went back to Taiwan at the end of May, so it's been over 2 months now.
Okay.
Yeah. And you been in South Africa the whole time?
I've been in my house the whole time.
Right. Yeah. Yeah, I haven't booked my ticket back to the US. Not sure when. So how's it going in Cape Town?
Yeah,
What's the COVID situation right now?
it's not great. It's yeah, I mean we're on the other side of a peak. I don't know whether it is the peak.
Okay.
And you know, the rolling 7-day average is coming down. We're kind of exiting winter, so the winter period is
Right.
one where pretty much everybody gets sick anyway. But the rest of the country is not doing particularly good. I think we're like number 5 in the total in the world at the moment.
Number in terms of what?
In total cases.
Oh, I see.
And we had a hard lockdown actually.
Uh-huh. So do you want to say a little bit more about your observation on Facebook for the COVID? Were you referring to the policy in South Africa or somewhere else?
You mean the we? The we was us, yeah. Yeah, it you know, it seems to me that that the there are these two ways of opening up, right? You either open up adiabatically and let things equilibrate and then then move on from there,
right?
Or you just open it completely up, everything goes pear-shaped, goes down again, and repeat. We have been opening up adiabatically, like very, very slowly, in fact, and then some really, in my opinion, poor decisions get made, and and there's lots of pressure to cave to the unions, various unions around the country, and basically anybody who has some leverage and pressure and the ear of the government, basically. So and then that's basically what happened. So there was the in the Western Cape where I live, the provinces run by a different governing body, a different governing party than the national government. And we were one of the only provinces to actually prepare during the lockdown for what was going to come. And so when they opened it up, we saw this rise, and then there's this peak, and now we're on the other side of the peak. And so hopefully it doesn't exponentiate from here. And certainly the weather's getting warmer, and as we leave winter, and I'm hoping that the situation gets better. But yeah, I mean, you can very clearly see the differences in governing style in the various different provinces. I guess as you can in the US and stuff.
Yeah. But based on what we are seeing in the Northern Hemisphere, it doesn't seem like the temperature is helping a lot. Is it?
No, I don't think so, actually. The only thing is that during winter here, it is definitely flu season, and everybody gets sick anyway.
Right.
This is the first year. So with my kids not being in school, this is the first year that I can remember where we're not like periodically sick during this year.
Right.
So there's that, at least. So let me see. 60 participants. Okay. I'm just gonna leave the screen for a couple of minutes and just get a cup of coffee, and then I'll join and we'll start.
All right, sounds good.
Shuheng, are you still there?
Yep, I'm here.
Hi, I'm Emmanuel. I'll be your chair.
Oh, hi. Nice to
just
meet
quick-
you.
Yeah, nice to meet you too. Just a quick question. Jeff said that I think he emailed you that you should expect a verbal reminder 5 minutes before and a minute before. Is that
Yeah,
okay,
yeah.
or would you prefer a message you over chat? I just find the chat isn't very visible at times. So
Oh, I think verbal might be better. Yeah.
I will just interrupt you. And,
Yeah, no problem. Yeah.
Okay.
All right. Thanks.
No problem.
Hi, Ron. It's good to see you. I think you're on mute, though.
Hey, Jeff, can you hear me now?
Yes, I can hear you now.
Yes. Pulled it off. You pulled it off.
Sorry?
You pulled it off.
Ask again at the end of the week.
Okay, and ask again.
Yeah. It's well, here we are.
Very good. So when are you planning to start?
Now.
Okay.
So I'm just
I
about
will
to.
mute myself and let you do your thing.
Right. Thank you. Okay. Emmanuel, can you see this?
Yeah, all good.
Excellent. So, depending on where in the world you're joining us from, a good evening, good day, good morning. My name is Jeff Mergen, and on behalf of all the organizers of this conference, I would like to extend a very warm South African welcome to all of you to String Math 2020. This year, it will be hosted by the Universities of Cape Town and Stellenbosch, respectively. And I have to say that my only regret is not being able to welcome you all here in person. But we have an exciting lineup of talks today and for the rest of the week. I want to acknowledge that the poster for this year's conference is inspired by Juan Maldacena's background from Strings 2020. And it's a typical African sunset. So let me quickly go through a couple of things before we start. As I said, we have an exciting lineup of talks today and for the rest of the week. Here's a picture of the lineup. You can also find the daily schedules on the website. I should say that as the talks are finished, we will attempt to put up the both the slides for each talk as well as the recordings of each talk linked to the website. The recordings will be available on our dedicated YouTube channel. We are live streaming at the moment, so if you now or in the future find yourself unable to join the Zoom, please feel free to join the live stream. You can ask questions in the live stream, and we'll try and convey them here as well. In addition to the plenary talks that we'll be having throughout the week, you'll notice that on Thursday evening, there will be a special public lecture given by the Leon Levy Professor and Director of the Institute for Advanced Study, Robert Degraff, on the unreasonable effectiveness of string theory in mathematics, largely talking about the interactions between string theory and mathematics over the years and as we go into the future. I would like to invite you all to sign up for the lecture. You can register for it on the website in this slide. That's http stringmath2020.com/public talk. And again, if you can't join the Zoom for that, you're welcome to join us on the same live streaming site as for the rest of this meeting. For anyone who's heard Robert Degraff speaking, you'll know that this is a talk not to be missed. And if you haven't heard him speaking, this is a talk not to be missed. So before we go on, I just want to make a couple of housekeeping announcements. We have a code of conduct that, if it's not up on the website at the moment, it will be in a few minutes. It largely revolves around being respectful of the other participants and the speakers in this meeting. It's up on the front page of the conference website. Please do read it and abide by the code of conduct. We'd like to make a special request that you keep questions till the end of each talk. And if you want to ask a question, and we do hope that you will want to ask questions, please use the raise hand feature in Zoom. And Zoom organizes raised hands chronologically. So the first person to raise their hand gets asked first. And we'll try and abide by that on our side, and wait to be called upon by the session chair. All participants will enter the room on mute. I'd like to ask you to please make sure that you remain on mute during the talk. It is quite distracting to have background noise going on. We will periodically be checking the participant list and making sure that everybody is on mute other than the speaker. You will notice, if you're not familiar with it already, that Zoom has a chat feature. Again, we'd like to encourage you to use the chat feature, but in a way that's not distracting for the rest of the participants and the speaker as well. So you're welcome to ask physics questions and pose them to anyone. Or if you have any organizational questions about the meeting, please do send a private message to one of the organizers. So on your list, you will see either myself, Jeff Murgan, or Nathan Moynihan. You're welcome to send us a private message regarding anything to do with the organization of the meeting. We will be setting up Slack channels shortly. There'll be a link on the website for the conference. Please do join the Slack rooms. They'll be organized by the talk. You're welcome to pose questions there, engage with the speaker, and we'll leave them up the whole week and possibly afterwards as well. So you're very welcome to continue discussions for as long as you want in that platform. We're going to have a conference photo, to the extent that these things exist these days, on Thursday before the public talk, and I would strongly encourage you to please do sign on to the Zoom room, and we'll take a Zoom selfie of everybody during the just before the public talk on Thursday. So that's all that I wanted to convey in terms of announcements. So let me then introduce you to our session chair for this first opening session, Emmanuel Manek, and Emmanuel will be running the session from now.
Thanks a lot, Jeff. We'll just wait a few minutes to start just after 2 o'clock with Shuheng.
Okay, in the meantime, maybe let me share my screen.
Yeah, okay, thanks.
All right.
Yeah, since it's 2 o'clock, maybe I'll just quickly reiterate what Jeff said. Thanks a lot for joining the first string math session. Thanks a lot to Jeff and the other organizers for organizing the string math conference, especially with these difficult circumstances. In case you've come in just in the last couple of minutes and didn't hear the announcement, please keep questions to after the talk. We've got 20 minutes set aside. And please keep your microphone on mute and use the raise hand button on Zoom to ask your question, and then I will pick you out in order for the questions. Okay, so with this, let me hand over to Shu Hang, who will tell us about continuum quantum field theory for fractals.
All right, thank you. As the first speaker, I would also like to thank the organizers for putting together the first virtual string math conference during such a challenging and unusual time. Also, I would like to thank you for giving me the opportunity to speak here. I'm going to talk about continuum quantum field theory for fractals. It's going to be based on these 3 papers with Nati Seiberg that we put out in the spring. This talk will be mostly about the 3rd paper. So let me get started. Common law states that starting at short distances with some lattice model with local interactions, there's an effective quantum field theory description at low energy or at long distances. A more limited version of this law is that every gap phase of a lattice system can be described by a topological quantum field theory at low energy. Now, topological quantum field theory has been studied extensively by both physicists and mathematicians. It captures the universal behaviors of these gap topological phases at long distances. However, this common law has been challenged by a large class of lattice spin models known as fractals. The fractal models can be gapless or can be gapped, and they do not seem to emit the standard continuum field theory limit. In particular, the gap fractal models do not seem to emit the TQFT description at low energy. In the talk today, we would like to extend the framework of quantum field theory to incorporate these fractal systems. As I said, fractal is really a large class of lattice spin models. It's not just one single model. But this talk, we will focus on a particular fractal model known as the XQ model. It's one of the most celebrated gap fractal model, and it's arguably the simplest one. We will restrict ourselves to 3+1 dimensional flat space-time. The quantum field theory we're going to find for the XQ model is not topological, but they have certain quasi-topological defects and operators. So even though they are not a standard ordinary TQFT, they do share some similar flavor as TQFT. I will talk a lot more about these quasi-topological defects later on. To begin with, let me just give you a definition and a lightning review on what the XQ model is. XQ model was first introduced by Vijay, Ha, and Fu back in 2016. It's a 3+1 dimensional lattice spin model. The space is a 3-dimensional cubic lattice. On each link of the lattice, there's a 2-dimensional Hilbert space. You can think about this 2-dimensional Hilbert space as a spin 1/2 qubit spanned by a spin up and a spin down state. Associated to each link, there's a pair of Pauli matrices, which I denote as sigma-1 and sigma-3. The subscript L tells us where these Pauli matrices live on. The Pauli matrices obey the standard commutation relations, so sigma-1 and sigma-3 anti-commute with each other, and they both square to 1. The total Hilbert space of this lattice system is the tensor product of the 2-dimensional Hilbert space associated with each link. So now I have a well-defined Hilbert space. I just need to write down a Hamiltonian that acts on this Hilbert space. So the Hamiltonian is designed the following way. Oops, sorry about that. So the Hamiltonian is the sum of 2 kinds of terms. The first term is called the A term, and the second term is called a B term. The A term is associated with a cube. That's the subscript C here. For each cube, there are 12 different links around the cube. And we multiply the sigma 1 associated with each link together. So this AC is a product of 12 different sigma 1s here. In the Hamiltonian, we sum over all such A terms over all the cubes in our three-dimensional cubic lattice. The second kind of term will be denoted as a B term. It's associated with a vertex V and a direction X or Y or Z. Here, let's look at BV associated with the Z direction, for example. So take this vertex V. There are 6 links connected to this vertex V. Out of the 6 links, we only take the 4 of them that are along the X direction or the Y direction, but not the Z. So this product is over the sigma 3 living on the links here and the links here. So there are 4 sigma 3 here. And similarly, we define our BX and BY. In the Hamiltonian, we sum over all these terms together. So at this point, I'm sure some of you are already lost in all this detail of the interaction, whether we multiply the sigmas on the links, in which direction, X or Y or Z. So let me reassure you that the details of these interactions are not going to matter for the rest of the talk. Later on, I will give a self-contained presentation of this model from the continuum field theory language. Here, I just want to be extremely explicit and give you the presentation of this lattice spin model. So now that we have a very explicit Hamiltonian, one can just go ahead and try to solve the spectrum numerically or analytically. I should say that all the local interactions, they're designed in such a way that all the terms in the Hamiltonians commute with each other. So 2 A terms obviously commute with each other because 2 sigma 1s commute. Similarly, 2 B terms commute with each other. It takes a little bit of work to check that if every pair of A and B also commute with each other. In any case, this is the definition of the model. And now you can solve it. And let me tell you what are the peculiarities of this model. So when you solve the whole spectrum, you will find that there are various strange phenomena in this model. And let me just outline a few. First of all, this lattice spin model for generic coupling is a gap model. So if you look at the spectrum at low energy, you have a lot of ground states, and then there's an energy gap, and then there's some excited state. The number of ground states, the lowest energy states, grows exponentially in the linear size of the system. Here, the capital Li is the number of sites along the xi direction. And we are assuming the periodic boundary condition. Explicitly, the ground state degeneracy of this lattice spin model is given by this formula. In particular, it becomes infinite in the continuum limit where we take the number of sites to infinite. So this is already a peculiarity that makes it seem impossible to admit a standard continuum quantum field theory limit because it has infinite ground state in the continuum limit. At this point, you might think this ground state degeneracy is just some very fine-tuned thing. Maybe if you change the coupling a little bit, or if you throw in some additional interaction, this ground state degeneracy might be lifted by all these deformations. But that turns out not to be the case. And that brings us to the second point, that the ground state degeneracy is robust, in the sense that any small deformations by local operators on the lattice cannot lift the ground state degeneracy in perturbation theory. This means that this ground state degeneracy is something really topological. So we have talked about this huge number of ground states. In addition to the ground states in our Hilbert space, there are also excited states. There are certain excited states or excitations that have energy localized somewhere in space. And these excitations exhibit restricted mobility. For example, there is a kind of excitation where the energy is concentrated around a point in space that's denoted by this red dot. However, you can show that there's no operator on the lattice that you can bring this excitation from point A to point B. Such an excitation is called a fractal, and this means that a single fractal cannot move by itself. However, if you have a pair of them carrying opposite charges, then they can move collectively in the direction transverse to their separation. Such a restricted mobility also seems impossible to be described by a continuum quantum field theory. So before we really attack the XQ model, as a warm-up, maybe let's consider a more familiar example, the Toric code. Toric code is also a lattice spin model, but it's much more familiar, and it has a continuum quantum field theory limit. So let me briefly introduce it. It's defined on a two-dimensional square lattice, so the dimension is one dimension lower than the XQ model. Again, on each link, we have a two-dimensional Hilbert space that you can think about it as a spin 1/2 qubit. And there's a pair of Pauli matrices obeying the same commutation relation as in the case of the XQ model. The Hamiltonian is a sum of two kinds of terms. This time, the A term is associated with a plaquette, and you multiply the sigma 1 around the plaquette. The B term is defined associated with a vertex V, and you multiply the sigma 3 on the links that are connected to this vertex. And the Hamiltonian is the sum of this local interaction. Let's put these two models side by side. They're in different dimensions. Their interactions are different. But if you just look at them for 5 seconds, you probably would think they look qualitatively similar. This turns out not to be the case. For example, the ground state degeneracy on a torus for the Toric code is just 4. It doesn't scale with the system size. By contrast, the ground state degeneracy for the XQ model scales exponentially in the linear size of the system. This is already one big difference between the two models. The excitations of the Toric code are the famous anyons. They are point-like excitations that can move arbitrarily in space-time. This is to be contrasted with the excitation in the XQ model, which are the fractals we just described and the lineons we will later encounter. And they have certain restricted mobility. The low-energy topological quantum field theory for the Toric code is the familiar 2+1-dimensional Z2 gauge theory. This is a topological quantum field theory that admits the Chern-Simons description involving two U1 gauge fields. So A and A has our one-form gauge field. I will say much more about the Z2 gauge theory later on, but it's a standard Chern-Simons theory. The goal of this talk will be trying to find out what is the low-energy quantum field theory description for the XQ model. It turns out that this quantum field theory is a certain kind of Z2 tensor gauge theory. Its Lagrangian also takes the form of a Chern-Simons type, or if you wish, the BF type Lagrangian. We have two kinds of gauge fields, and the Lagrangian is the gauge fields of one kind multiplied by the field strength of the other kind. I will explain the notations later on. But before that, let me review the case of the Z2 gauge theory first. So how do we describe the 2+1-dimensional ordinary Z2 gauge theory? One way to describe it is to start from an ordinary U1 gauge theory with a one-form gauge field A with a vector mu index. So here, let F mu nu be the field strength 2 form of the gauge field. And F mu nu is just the standard Maxwell term in the 2+1D Lagrangian. We introduce a real scalar field, phi, that is 2π periodic. It is a charged 2 Stockerberg field that's going to Higgs our U1 gauge group down to Z2. The gauge transformations acts on the Stockerberg field by shifting it by 2 times the gauge parameter alpha. Here we have 2 because I assume the Stockerberg field to have charge 2. And we introduce this Higgs coupling. At low energy, it is sometimes more convenient to dualize the Stockerberg scalar field phi to another one-form gauge field A hat mu. And then we can write the low energy description of this Higgs Lagrangian in terms of a Chern-Simons Lagrangian. The Chern-Simons Lagrangian involves two gauge fields, the original U1 gauge fields A, and the A hat one-form gauge field that comes from dualizing the scalar field phi. So to put those formula in words, the way we obtain the Z2 gauge theory is to start from a gauge theory of a one-form gauge field A mu with an ordinary U1 gauge symmetry, and we Higgs the gauge group down to Z2. That was for the Toric code. Now we apply the same strategy for the X model, except that in step 1, we are going to start with a gauge theory whose gauge fields are going to be denoted by a capital A, and it has an exotic dipole U1 gauge symmetry that I will discuss momentarily. In step 2, we subsequently Higgs this dipole U1 gauge symmetry down to Z2. There are various new elements in our quantum field theory for fractals, and they're essentially unavoidable. First of all, our quantum field theory are non-relativistic. In fact, they are not even rotationally invariant under the SO3 continuous rotation group. We will only have the rotation group generated by 90-degree rotation and the continuous translations. I will say more about that in the next slide. Second, our quantum field theory exhibits various exotic global and gauge symmetry. Third of all, which is perhaps the most bizarre feature of this exotic quantum field theory, is that various discontinuous field configurations are going to play an important role in the discussion of our systems. Let me say a little bit more about the space-time symmetry. Our model is in 3+1 dimensions. The space-time symmetry includes only the 90-degree spatial rotations, which generates the cubic group. Here we are ignoring the parity and reflection. The cubic group is isomorphic to the permutation group of 4 elements, S4. In addition, we have continuous translations in space and in time. In ordinary relativistic quantum field theory, fields are in the irreducible representation of the Lorentz group. That's why we have scalars, we have vectors, we have higher forms, we have spinors, etc. Since the only available rotation groups to us are the 90-degree spatial rotation group, the cubic group. So our fields are going to be in the irreducible representations of the cubic group S4. You can easily look up the irreducible representation of S4, and there are 5 of them. So again, don't worry too much about the details of these irreducible representations. All these indices are not going to matter too much down the road. But the only message I would like to convey here is that later on, when you see all these fields, there are inserted representations of this S4 representation, of this S4 group. Let me just quickly go over what are the representations that are going to be relevant for us. So of course, we have the trivial representation. It's one-dimensional. It's going to be denoted by 1. And then we have a 3-dimensional representation, which you can think about it in the following way. We can embed S4 into the SO3 group. The SO3 has a vector representation. The 3-dimensional vector representation of SO3 reduces to this 3-dimensional representation of S4. The SO3 group also has a 5-dimensional traceless symmetric tensor, which decomposes to 3' plus 2 under S4. Here, this 3' is another 3-dimensional representation of the cubic group that's different from the vector. You can think about it as the off-diagonal part of a traceless symmetric tensor. So we have Tij, but importantly with I not equal to j. So there are only 3 of them, Txy, Tyz, and Tzx. In addition, we have a 2-dimensional representation that you can think about as the diagonal traceless part of this tensor. Finally, we have a sign representation, 1', that's not going to play any role in this talk. Again, the details are not going to matter, so don't panic if you cannot memorize all these representations. So now let's come to the quantum field theory for fractals. We will start with step 1, a gauge theory with a dipole U1 gauge symmetry. This gauge theory has been studied extensively in the condensed matter literature. It has a temporal component, several spatial components. The temporal component is denoted by A0, and it's in a trivial representation of the cubic group S4. There are 3 components for the spatial part. They are in the 3' representation of S4. And let me just remind these are the off-diagonal part of a symmetric traceless tensor. So here I is never equals to j. We only have 3 of them, axy, ayz, azx. And they have the following gauge transformation. We refer to this gauge transformation as a dipole gauge symmetry because the gauge transformation for the spatial components of the gauge field involve 2 derivatives here. Here alpha is the gauge parameter, which is a real scalar. From this gauge transformation, you can build the gauge invariant electric and magnetic field. They are in their respective S4 representations. Now we can build a Lagrangian for this gauge field, which we will refer to as a U1 tensor gauge theory. The Lagrangian is the sum, is the difference of the electric square and the magnetic field square, similar to what we usually do for the Maxwell Lagrangian. Gauss law takes an exotic form where we have 2 derivatives hitting on the electric field. This U1 tensor gauge theory turns out to be a gapless fractal model. But this is not the SQ model, which is gap. And that brings us to step 2, where we are going to Higgs the gauge group from U1 to Z2. To do the Higgsing, we introduce an additional real compact scalar field phi that you can think about it as a charge 2 Stokesberg field. The phi is 2π periodic. So in addition to the Lagrangian for the U1 tensor gauge theory, we now add a coupling to this charge 2 Stokesberg field. The gauge transformation for the gauge transformation shifts phi by 2 times the gauge parameter, where this 2 comes from the charge of this Stokesberg field. Again, at low energy, it's convenient to dualize the real scalar field phi to a gauge field that will be denoted as A hat. This A hat gauge field has several components and some complicated indices. I will explain their S4 representations momentarily, but for now, let me just write the final Lagrangian for you after we dualize the Stokesberg field and go to the low energy. This is our final Lagrangian, and it takes the form of a transimens type or BF Lagrangian. It involves 2 sets of gauge fields, the original A that we have just discussed. These are their S4 representations, and a new set of A hat gauge fields that I remind you comes from dualizing the charge 2 Stokesberg field phi. The temporal components of the A hat gauge fields is in a 2-dimensional representation. The spatial component of the A hat gauge field is in the 3' dimensional 3' representation of S4. And the Lagrangian takes the form of the gauge field of one kind multiply the field strength of the other kind. So it's of the transimens or BF type. The gauge symmetry schematically take this form, where I have suppressed all the indices. Now let's just compare the ordinary Z2 gauge theory in 2+1D with our 3+1D quantum field theory that we refer to as the Z2 tensor gauge theory. In both cases, we started with a U1 gauge theory with a Maxwell type Lagrangian. We introduced a real scalar field that Higgses the U1 gauge symmetry down to Z2. These are denoted as phi in both cases. And then we dualize the scalar field to another gauge field that we call A hat and write a low energy Lagrangian in a transimens form. it is straightforward to generalize to Zn tensor gauge theory, where we simply replace the coefficient 2, which comes from the charge 2 Stokesberg field. We replace the 2 by n here. Conversely, you can ask, suppose someone hands you this Lagrangian with the corresponding gauge transformation. How do you know the coefficients or level here has to be an integer? It turns out that the level n is quantized by a discontinuous large gauge transformation on a Euclidean 4 torus. It takes the following form, where theta is a Heaviside theta function, is the step function. And the quantization of this level really comes from such a discontinuous field configuration, and this highlights the importance of discontinuous field configurations in our quantum field theory for fractals. So now we have a continuum Lagrangian that we propose to be the low energy limit of the X-cube model. Does this do the job? Let's try to reproduce all the peculiarities of the X-cube models that we review in the beginning of this talk. Let me quickly remind you what are the 3 peculiarities that I mentioned in the beginning. First, there's a huge number of ground states when you quantize the systems on a torus. The ground state grows exponentially in the linearness of the system. We will return to this large ground state degeneracy towards the very end of the talk. The second peculiarity is that the ground state degeneracy is robust. And the third is that various excitations or excited states have restricted mobility. Let's start with point number 2, the robustness of the model. Small perturbations on the lattice at short distances become local operators in the long distance quantum field theory as we do the RG. If these local operators are relevant, they typically destabilize the system and making the system not robust. This is our continuum Lagrangian. We can then derive the equation of motions from these Lagrangians, and you'll find that the equation of motions sets all the local operators, which are the gauge invariant electric and magnetic fields, 0. So these are the equations of motion. So there's no local operator in this Lagrangian at all. Therefore, the Z2 tensor gauge theory is robust because there's nothing we can add to the Lagrangian to deform the theory. So the absence of local operators of our continuum Lagrangian explains the robustness of the X-cube model. This is very similar to the Chern-Simons theory and to the more general topological quantum field theory. So this is that's the second point. Now let's come to the third point, where there are excitations of the X-cube model exhibiting restricted mobility. Let me remind you that our continuum field theory captures the low energy behavior of the lattice spin X-cube model. In the low energy, we only see the ground state of this lattice model. So in the Hilbert space of our continuum field theory, we only have the ground state. We do not see all those excited states. Then how are we going to capture the restricted mobility of the excitations? The excited states, as we go to the low energy, will not be states in the Hilbert space. Rather, they will become defects of our continuum field theory. Recall that our Z2 tensor gauge theory has 2 sets of gauge fields, A and A hat. Let's start with the defects of A. Here I write the gauge transformation of the gauge field A again. This, as we said, there's no gauge invariant local operator because of the equation of motion, but there could be gauge invariant extended defect or operator. The simplest one is a line defect. So it's an integral in time from past infinity to future infinity of the time component of our gauge field A. You can easily check that this is a gauge invariant line defect. It describes a single fractal in the probe limit that just sits at one point in space, not moving at all, from past infinity to future infinity. In ordinary gauge theory, we can write down a more general gauge invariant line defect that has support on a general space-time curve. But here, in ordinary gauge theory, we do that by integrating the one form A along a general space-time curve. But here we cannot do that because we don't have a connection. We only have A0, but not AX, no AY, no AZ. We only have this AIJ components whose gauge transformation comes with two derivatives. And it takes a little bit of work to convince yourself you cannot write down a gauge invariant line defect that has supports on a general space-time curve using these gauge fields. And that explains the restricted mobility of a single fractal. What you can do is to take a pair of fractals and move them collectively. Such a motion is captured by this gauge invariant Wilson strip defect. There are a lot of indices here, and don't worry about it. The only thing that matters is what we are integrating over. So here we are integrating over a curve C, T and X and Y space-time. So that's this curve on the TXY space-time. And we further integrated in an interval in the Z direction from Z1 to Z2. So the total geometry or topology of this Wilson strip is the direct product between this curve C in TXY and the interval in Z. So this is a strip in space-time. And you can check that this is invariant under the above gauge transformation. This describes the motion of a pair of fractals moving collectively on the XY plane. You can move on a plane is usually referred to as a planon. Therefore, we have seen that the restricted mobility of fractals is explained by the gauge invariance of the defect in our low energy continuum field theory. Now let's also talk about the defects from the A hat gauge field. Here I write the gauge transformation for the A hat gauge field. Again, don't worry about the indices. It's not going to matter too much in the following. The defects for the A hat gauge fields corresponds to the Linear excitations of the XQ model. Linears comes with 3 different species associated with the X or Y or Z direction. A single linear of species X can move along the X direction, but not in Y or Z. And so the word line of such an X linear will be like this. This is going to be a curve on the TX plane, but at a fixed Y and a fixed Z. Such a motion is captured by this gauge invariant defect. Again, the indices and the integrands is not terribly important. All you have to keep in mind is that this is an integral along a curve C hat on the TX plane at a fixed Y and Z. So here's the cast of characters in the XQ model. We have fractals and linears that are represented by Wilson defects of our gauge fields A and A hat, respectively, in the continuum Z2 tensor gauge theory. These Wilson defects are very similar to the anyons of the ordinary Z2 gauge theory, or to the more general topological quantum field theory. The ordinary anyons in topological quantum field theory are topological, in the sense that if you deform the word line of the anion a little bit without passing through any other operator, it's not going to change any correlation function. Are our fractals and linears topological? Not quite. So let's look at the Wilson strip, the strip operator made out of the A gauge field. It's not completely topological because, first of all, its shape is dictated to be such a strip. And if you change the Z position, for example, if you change the Z1 or Z2 a little bit, that's going to give you a different defect than the previous one. In general, if you change the Z2, the new defect will have a different correlation function compared with the old one. So it's not completely topological. However, since the electric and magnetic field of the gauge field A vanish, the Wilson strip is topological in the deformation of this curve C in T and X and Y. So you can freely deform this curve in the T and X and Y space-time with Z1 and Z2 fixed. This deformation is not going to change any correlation function. So to summarize, such a Wilson strip describing a pair of fractals is topological in T and X and Y, but not in Z. For this reason, we will call it a quasi-topological defect. We can consider a special case of this defect where the curve C is at a fixed time. Then it's not a defect, but an operator, a strip operator, to be more precise, acting on our Hilbert space. In fact, this is a symmetry operator generating a Z2 dipole global symmetry. This is a certain kind of exotic global symmetry. In quantum information theory, this is known as a logical operator. Similarly,
sorry, just
thank you.
5 minutes. Okay.
Okay, thank you. Yeah, similarly, we can consider the defect of the A hat gauge field. Again, it's not completely topological because this defect is constrained to be on the TX plane. It cannot move perpendicular to the screen. But since the electric and magnetic fields of the A hat gauge field vanished, this hatted Wilson line is topological in the C hat curve. So you can freely deform this curve on the TX plane. So it's topological in T and X, but not in YZ. Again, at a fixed time, it is a line operator generating certain exotic Z2 tensor global symmetry. It is another kind of logical operator in the context of quantum information theory. So now we are finally ready to talk about the large ground state degeneracy of this model. First, the ground state degeneracy is infinite in the continuum limit. So to make sense of this formula, we have to regularize it on a lattice. As we just discussed, the continuum limit of the XQ model has two kinds of exotic global symmetries. The first kind is generated by a line operator that we refer to as a Z2 tensor global symmetry. The second kind is generated by the strip operator that we refer to as a Z2 dipole global symmetry. The important aspect of this global symmetry is that there's a non-trivial algebra between these two global symmetries. You can show that by choosing an appropriate basis. The symmetry operators form 2Lx plus 2Ly plus 2Lz minus 3 pairs of Heisenberg algebra. Here, by Heisenberg algebra, I mean an algebra with two elements A and B obeying such an non-trivial commutation relation. An important fact about this Heisenberg algebra is that it does not omit a one-dimensional representation. The minimal representation of a Heisenberg algebra is two-dimensional. Our ground states are in the minimal representation of this many Heisenberg algebra, and that explains this exponentially growing ground state degeneracy. So to summarize, the three peculiarities of the XQ model on the lattice are explained from the point of view of a continuum quantum field theory. The large ground state degeneracy is explained by the exotic global symmetries and their non-trivial algebras in the continuum quantum field theory. The robustness of the model is explained by the absence of local operators. The restricted mobility is explained by the gauge invariance of the Wilson defects. So to conclude, we have extended the framework of quantum field theory slightly to incorporate fractals. Our final Lagrangian is the Z2 tensor gauge theory. It's the low energy limit of the XQ models. It takes the form of a Chern-Simons type, and it captures all the universal peculiarities of the XQ model. It's not a TQFT. However, its defects and operators are topological in some direction, but not in others. So it has some similar flavors as an ordinary TQFT. There are several future directions. First, as I said, Fractal is not a single model. It's a huge family of lattice spin models. And it will be interesting to put all these lattice spin models in the context of continuum quantum field theory. In a paper to appear with Gorentalon, Lam, and Nadi Seiberg, we find a continuum quantum field theory for another famous fractal model known as the checkerboard model. Second, it would be more interesting to place the theory on more general manifolds, and a lot of work has been done in the condensed matter literature along this line. Third, it would be interesting to study certain braiding processes between the fractals and the linears, or the more general quasi-topological defects in this class of model. Finally, ordinary TQFT can be axiomized into the framework, into the mathematical framework of the unitary modular tensor category. And this gives a mathematically rigorous, precise question of classifying ordinary TQFT. It's natural to ask whether the gap fractal models can be formulated under a similar mathematical formalism. So I think we're still at a very early stage of exploration for these fractal models. And I think there are many more interesting developments to come. All right, I think I have used up my time. Thank you very much, and please stay healthy. Thank you.
Yeah, thank you very much. I'll just unmute people. Please feel free to clap for Shuhang.
Thank you.
You anxious?
Yes.
Hey, thank you very much, Shuhang, for this very interesting talk. So let's move to the questions now. We've got a good 20 minutes, so hopefully plenty of time for people to ask questions. There was a question already from Hank Chen in the chat. I think it was partially answered by Nathan, but I'll just get Hank to ask again. I think he wanted a reference. Hank, if you can unmute yourself.
Yes, hello. Can you hear me?
Yep.
Okay, so thank you, Shuhang, for the very interesting talk. I've always been very interested about these fractal things. So I was just wondering if there is some reference that talks in detail about the fusion and braiding between the lineons and the planons in a fractal model.
Right. I mean, there's really a large literature, especially in the condensed matter physics, about the XQ model. And I believe you can pretty much find a fusion between the fractals and lineons in every one of them. In some of the papers, they have defined certain braiding processes, but I don't remember the references on top of my head, but I can send you in private.
Okay, sounds good. Thank you.
Okay, if there are any other questions, please use the raise hand button. If you go to the chat in Zoom, there will be a button above where you can type the chat, and then I can pick you out. Maybe I don't see a question yet, so while people are working out how to do this, maybe I can just ask a quick question. So what you were talking about was very much focused about this X-cube model.
Yes.
But how general is the story? I mean, in particular, is it that whenever you have one of these tensor gauge theories and you go to a Higgs phase, you get one of these gapped fractal models, or is this just a special example where this works?
Yes, well, I think this is also the question we are studying, like how general this recipe is. And so far, well, we don't have any rigorous theorem proving in what kind of model our recipe works. But it seems to work quite broadly. So for example, as I mentioned on this slide, we are now writing a paper on generalizing the same recipe to another fractal models. So there might be some novelties in other class of model that we haven't encountered yet, but so far I think it applies to a very large class of models.
All right. Okay. Thank you. So any other questions from other participants? I've just been told that you have to click on the participant button on Zoom, and then you will see these buttons like raise hand. Okay, I've got a question from Ali Shepa. If you can just unmute yourself, Ali.
Hi.
Hello.
Thank you for the talk. I'd like to ask if, so you wrote down 5 different representations of S4.
Yes.
So they all seem quite bosonic in their nature.
Right.
there
So
such a thing as a fermionic fractal model?
Yeah, so let me answer that. Yeah, so you see, the XQ model start its life as a lattice spin models. The degrees of freedom are some spin 1/2 qubit. So this model is very much a bosonic model, and our continuum theory is a bosonic model. There are certain fermionic fractal models on the lattice discussed in the literature, and we are not there yet. And I think it's a very interesting generalization that we want to do.
Okay.
Does this answer your question, Ali?
Yes, thank you.
Yeah, I'll mute you again. Please go ahead. If there's any further questions, just raise your hand, or given we don't have a huge rush of questions right now, you can also just unmute yourself, hopefully not causing chaos. Maybe I can ask another naive question. So
yeah.
Your starting point was a U1 tensor gauge theory.
Yeah.
Is there something like a non-abelian version of these tensor gauge theories, and can they play any role here, or do you always have to start with U1?
I think there might be. I haven't studied it thoroughly, but there are some literature about it. Yeah, I think it will also be very interesting to generalize. Yes. Yeah. So as I said, I think there are many different directions to generalize. Yeah, and we haven't done all that yet. But yeah, that's also one very interesting direction.
Okay, thanks.
Yeah.
Maybe just another thing I was wondering, at the beginning you gave this parallel or not parallel between the Toric code and what happens
right.
in the 3+1 dimensional model.
Right.
So is there a 2+1 dimensional analog of the X-cube model? So something which is more similar with some tensor gauge theory, or does that not work in your dimensions?
The answer to this question really depends on which background you come from. So I can say a little bit more about that. So it really depends on what do we mean by a fractal model. And to the best of my knowledge, it has not been defined in a very general or mathematically rigorous way. So different people might mean different things when they refer to fractals. And as I mentioned in the very beginning, there are various peculiarities of this particular XQ model. The large ground state degeneracy, there's a robust ground, and it's robust. And then there are some restricted mobility. If you are willing to give up on the robustness of the model, which high energy physicists do not care that often, then the answer to your question is yes. There is a 2+1 dimensional lattice spin model that is not robust, but share the other 2 peculiarities of the XQ model. But for condensed matter physicists, they are typically more interested in models that are robust, such as the Toric code or the XQ model. Then, to the best of my knowledge, you have to go to 3+1 dimensions to have a fractal model in this sense.
Okay.
And in a way, this jumping dimension, but this dimension you can also see in other places of the talk. So in ordinary 2+1D relativistic system, a real scalar field is dual to a one-form gauge field. And here in 3+1D, for our more exotic theories, a real scalar field is also dual to a gauge field.
Right. Okay. And then in this 2 + 1 dimensional analog dimension, which is not robust, it's not quite a tensor gauge theory you would be writing down then.
Well, it's in different dimensions, but it's actually very similar. So the gauge field, it's basically the same, but now you only have A0 and AXY.
Okay.
Right. Here, IJ runs over X, Y, and Z.
Sure.
But now it's only AXY. So yeah, indeed, in our paper, we also call it a tensor gauge field, even though the spatial components has only one component. Yeah.
Okay. Great.
Yeah. So it works in a very parallel way.
That's nice. Thank you.
Yeah. Yeah.
So yeah, if I'll just let other people raise their hands if they want to ask a question. Right. I don't see any further questions, so maybe this is just a good opportunity to thank you once again, Shuhang, and then we have about 9 minutes, I believe, before the next talk, which is starting at 3. So thank you very much, Shuhang.
All right. Thank you. Thanks.
Hi, Thomas.
Hi, Jeff.
Okay, good. I've made you co-host, so you
Perfect.
can.
Yeah, thank you.
Yourself.
And are my slides already visible?
Yep.
Okay, perfect. And you can hear me well?
Yes, we're good.
Good. Then I think I'm ready. That's good.
Okay. So got about 8 minutes or so.
Can you see the mouse if I'm moving it on the slides?
Yes.
Yeah. Okay, good. Perfect.
So hi, Thomas. I'm Emmanuel. I'll be chairing your talk as well. If it's okay with you, I'll give you some visual, well, I'll interrupt your talk at 5 minutes and 1 minute to the end, just to let you know.
Please do that.
Sure. Okay, since it's approaching, well, 3 o'clock where I am, I'll just welcome the people who have joined us in the last couple of minutes. Please keep yourself muted during the talk, just so there's no background noise, and please keep your questions till after the talk so that we don't disturb the flow of the talk. If you have a question, there is a raise hand feature on Zoom. If you click on participants, you should see some buttons, and one of them is raise hand. Then I will be able to see that you have a question, and I'll pick you out in the right order at the end. Yeah, and other than that, thanks to Thomas Kreutzig for giving us the next talk on W-algebras.
Hello, everybody. Firstly, let me thank the organizers for inviting me. I wish we could have done this in person, but that's what it is. I'm talking about W-algebras, and W-algebras is another name for vertex algebras that have fields of higher conformal weight. And over the last 5, 6, 7, or many years, they have often appeared in 2D, 3D, and 2D, 4D correspondences. And the features of these W-algebras that appear in these correspondences are quite new and very interesting. And this talk is about 2 such features. One of them is Triality, which appeared in the story of vertex algebras at the corner of Davide Gaiotto and Miroslav Rabczak. And this is probably a fairly well-known story. And then there's a second one I'd like to talk about, which I like to call the UROT, or translation of W-algebra property. And this has appeared prominently in the story where VOAs appeared as invariants of 4 manifolds by Boris Fagin and Sergei Bukov. And I plan to split this talk into 3 parts. So first I will just give a light introduction, and then I'll come to these 2 problems. And so vertex algebras are the mathematician's name for the symmetry or chiral algebra of a 2-dimensional conformal field theory. And so as such, since these 2-dimensional conformal field theories describe the world sheet of a string propagating in space-time, they appeared quite prominently in string theory. Now, from a mathematician's point of view, you would say understanding a conformal field theory is more or less the same thing as understanding the representation theory of the underlying vertex algebra well. So this means the VOAs appeared first in the 1980s, and they at the very same time appeared also quite meaningful in mathematics. And namely, at that time, one of the important problems was the monster-moonshine conjecture relating the monster group with modular functions. And it turned out this moonshine conjecture could be proven using the bosonic string construction associated to a very special vertex algebra that had this special group, the monster group, as automorphism groups. And then maybe besides the special problem, VOAs became quite important for mathematics because the representation theory, as we heard in Shu Heng's talk, are modular tensor categories. So they are very nice tensor categories that, for example, give rise to the topological field theories and other structures. And in generality, VOAs are somehow a nice black box that connect to very interesting geometry, topology, number theory, and also other mathematics. And this has continued, but in the last year, it was not string theory that was so much in the focus, but more of a 3-dimensional and 4-dimensional gauge theories. And the shift of type of VOAs we are interested in has changed. While in the old times, one usually has been looking for unitary, rational, conformal field theories, so that they have this nice modular tensor category as representation theory. Everything is nice and well structured. Now, in the modern VOAs have much wilder representation theories, not semi-simple anymore, not unitary anymore, not necessarily finitely many simple objects. And also the type of questions we are asking about vertex algebras are very different. And this talk is about 2 of these new appearances and new features of vertex algebras. And so all vertex algebras I know are associated to affine Lie superalgebras. What this means is the very basic, if you wish, vertex algebra that you can construct is you take your favorite Lie superalgebra, and then there's then you go to the affinization and you get a vertex algebra or vertex superalgebra. And then there's a set of standard constructions that you can iterate, and all known VOAs you get by an iteration of this standard construction, at least all the ones I know. And these constructions are, for example, extending the vertex algebra, or taking invariant subalgebra, invariant under some group, or with the action of another vertex algebras, or something like BRST cohomologies. And we will actually talk in this talk, be concerned with a mix of these constructions. In this slide, I recall some basics about a vertex algebra associated to a Lie algebra, or more general, to a Lie superalgebra. These are called affine vertex algebras. and they are associated to a Lie superalgebra and a bilinear form. So usually you normalize this bilinear form in a standard way, and then consider multiples of this bilinear form, and the multiple is called the level of the vertex algebra. And these vertex algebras are strongly and freely generated by fields associated to a basis of the Lie superalgebra with this operator product algebra. And now usually you don't, then there's a universal VOA, which is called VKG, and this doesn't need to be simple, and then often or usually you pass to the simple quotient. In the old literature, people usually have been concerned with the Wess-Zumino-Witten theory, which is the case when this integer is, when this level is an integer, this scaling of the bilinear form. Now, once you have a vertex algebra associated to a Lie algebra or Lie superalgebra, there's a very nice construction which gives you a zoo of more such structures. And they are associated again to your Lie superalgebra, and then to a choice of a nilpotent element in G. And then it turns out that there exists a complex. That means there exists a ghost superalgebra, just a bunch of fermionic and bosonic ghosts that are specified by the choice of nilpotent element, such that the affine vertex algebra times this ghost superalgebra is a complex, and the corresponding homology is called the W-algebra associated to this Lie algebra and this nilpotent element. This includes the affine vertex algebras. That means this includes the vertex algebras that are associated to Lie algebras. Namely, you just take the zero nilpotent element. The one that most people are familiar with is the principal nilpotent element. So then that's then the usual W-algebra. For example, the usual W-algebra associated to SLN is of type 2, 3, 4 up to n. This means it's generated by one field in each conformal weight 2, 3 up to n. For example, if I take SL2, I just have a single field in conformal weight 2, and this is the Virasoro algebra. And historically, if you look at the literature, people have almost exclusively been concerned with these principal W-algebras, but modernly, this is not the case anymore. Nowadays, we are interested in all these W-algebras, and actually also superalgebras. And not only, of course, the W-algebras, but also their modules. And they have actually very rich and interesting representation theories. I'm not at all talking about this. I'm only introducing here the very basic class of modules. So what is the basic class of modules of a Lie algebra? That are their integrable representations. And so what can I do? I can lift these to a module to the affine Lie algebra. These are then called the Weil modules. So what I do is I take the integrable representation, the finite dimensional representation of my Lie algebra, and I just let all positive modes of the affine Lie algebra act as zero, and then let the negative part act freely, and then I get a module that is called the Weil module. So it just has as its top level this finite dimensional representation of the Lie algebra, and then freely induced by the negative modes. And only this type of modules we are concerned about in this talk. The category of these types, and then if I have these modules, I can of course also look at the corresponding homology, and this gives me automatically a module for the W-algebra. So these are these modules. And I will just denote them by M psi F lambda, which encodes all information about these modules. So lambda is the highest weight of the Lie algebra which it comes from. Psi is the level shifted by the dual Coxeter number. This is a notation coming from physics, which is enormously useful, I find. And F indicates the nilpotent element. That means which W-algebra we are looking at. And I denote the category of those modules, or better, the category whose simple objects are these modules, by KL. And then with these indices, where KL stands for Kashtan-Lustig. Why? Because Kashtan-Lustigs were the ones that prove that in the case of f equals 0, in the Lie algebra case, that this category has actually the structure of a ribbon category, of a braided rigid tensor category. And this is a statement that you actually believe to be always true, or at least for generic level to be true. But it's one of these statements that are very hard to prove, and you actually will believe much more to be true. If you actually believe that which f I put there, all these categories are ribbon equivalent. This is a conjecture that nicely connects to quantum geometric Langlands, and but we will not talk so much about this in this talk. Then, so the W-algebras, they are constructed as a cohomology or a homology. And this is one way of how I get out of a given vertex algebra a new one. And another way is the coset construction. I just take a large VOA, let's call it V. I take a subalgebra W, and then the subalgebra of that commutes with W is called the coset VOA. In physics, it's usually written as a quotient V over W. And what is interesting is that these cosets can also be realized as relative semi-infinite Lie algebra cohomologies, at least when the scalar, this level, is generic. And this is I view it at least as the mathematical formulation of gauged Weston-Witten models. And yeah. Now, in this talk, I'm interested with our Lie algebras of interest are of type A. This means they are of type SLN or of type SLN/M. And the nilpotent element we are interested in is called Fn, M. So it turns out that nilpotent elements or equivalence classes of nilpotent elements in SLN are parameterized by partitions of the integer n. And so here my integer is n plus m, and I take the partition n plus m is equal to n plus 1 plus many ones. If you view this as a Young diagram, then this is a small hook, one column and one row. And then there are a few special cases. Of course, you can take m to be 0, then this is just the partition n is equal to n, which is the principal nilpotent element. So in this case, one gets the normal, the usual W algebra of SLN, the Wn algebra. If you take m equals 1, you get the W algebra that has been studied a lot by Boris Fagin and Alyosha Semikhatov. So it's often called also the Fagin-Semikhatov algebra. If you take the other extreme case of n equals 1 actually, then you get the affine vertex algebra, and then another maybe relatively well-known case is the case of minimal W algebras. Minimal W algebras are those which only have fields in conformal weight 1, 3/2, and the Virasoro field. So this is maybe as a summary, the type of W algebras we are interested in are associated to SLN, and the nilpotent element is a small hook, the Young tableau that has one column and one row. And the same type of construction also works for the super algebras. And again, we can, in this case, the nilpotent elements are parameterized by super partitions. So that means if I look at SLN/M, means super trace with n plus m times n plus m matrices, then any partition of n/m gives me a nilpotent element and a corresponding W algebra. And we are interested in the ones of partitions of this type. namely that n/m is of type n/1 and then only ones. Again, we have a few well-known cases: principal W-algebras, principal W-superalgebras, affine vertex superalgebras, and minimal W-superalgebras. Now, while the principal W-algebra of SLN has generators in conformal weight 2, 3 up to n, these W-algebras all have the property that they also have fields of conformal weight 1. That means they have an affine vertex algebra subalgebra. And the setup is such that all these examples for the superalgebras as well as for the Lie algebras have a subalgebra and affine vertex algebra of type GLM. So this because we have M1s appearing here in the partition corresponding to the nilpotent element. So this means they have an affine subalgebra, and this means I can take the coset. I can restrict to the subalgebra that commutes with this W-algebra. And I just give them some names, C psi of n, m for the cosets coming from the W-algebras, and D psi n, m for the cosets coming from the W superalgebras. And don't worry about these special cases. It's just if I take m and or n to be small, then the construction is a little bit different. This is not important for the case. The important thing is the generic case, which is the top one in each of the two. Okay, so why did I do this introduction? Well, of course, I did it because these algebras appear very prominently in one 2D, 4D correspondence. And more generally speaking, the correspondences, at least where I get my intuition from, are AGT correspondence, which is a correspondence between n = 2 supersymmetric 4D gauge theory to Toda field theory. So Toda field theory is a conformal field theory that has Wn algebra as symmetry, so the principal W algebra as symmetry, and then actually the central connection in this talk are the corner VOAs of Miroslav Rabczak and Davide Gagliotti, and so they appear in the connection to n = 4 supersymmetric 4-dimensional GL twisted gauge theories. And then also these also appear in the story of Boris Fagin and Sergei Gukov of VOAs and 4 manifolds. And all these connections of VOA to, so in all these stories, the vertex algebra and also its module category or other invariants of the vertex algebra appear as kind of meaningful invariants of the gauge theory. And this is a general theme. The VOA is a 2D thing, so a VOA is of course much easier to understand. As a 4-dimensional gauge theory, it's still very difficult to understand. And so if I can make progress in my understanding of the VOA, of its representation theory, or other properties, then maybe this will teach me something for physics. I will now, I'm concerned with the converse. I'm taking predictions from physics and I'm trying to understand them in a vertex algebra setting. And the vertex algebras of interest are the Y-algebras that were introduced by Miroslav and Davide, and also studied a lot by Miroslav and Thomas Prochaska. So these are called Y-NML algebras, where NML are non-negative integers. And then there's also an index psi, which is the coupling of the gauge theory. And they appear at junctions of interfaces in these 4-dimensional gauge theories. And on each, and the associated gauge groups are UN, UM, and UL. So here we take gauge groups of unitary type. There's a very similar story for gauge groups of orthosymplectic type. It's a little bit more complicated. And then it's not only the VOA that is associated to the setup, But then the line defects on the interfaces are associated with, so you think about it as modules are associated to the line defects, and these line defects categories, it makes sense to call them Kastanlustig of n/m, meaning Kastanlustig of SLN/m, whatever this is supposed to mean. And then one can have webs of Y-algebras, and I will give you some pictures before I go on. So this is my drawing of a Y. You just draw your Y, and then each face you label by an integer, n, m, and l, and each line segment you label by a category, and this category you give the name Kastanlustig, and then first integer, the integer on one side / the other one. The way you think about it is that this Y and ML algebra is some very new and complicated vertex algebra that has 3 each other centralizing categories as categories of modules, namely somehow categories associated to the Lie superalgebras n/m, m/l, and n/l for some level, which I omitted here in the picture. And the picture for the Y for the web is you just connect many Y's, and then and again do the labeling. Each face is labeled by a non-negative integer. So here n, m, l, r, s. And at each corner you have a corresponding Y algebra, where the indices are the corresponding integers, the corresponding gauge group labels. And then to each line segment you attach a category. And the picture is that, so now naively you might maybe think the vertex algebra you associate to it is just the tensor product of these 3 Y algebras associated to this corner. But these Y algebras share common categories, and then you can extend along them. So this means a web configuration like this one has a large extension of the tensor product of 3 Y algebras. And now you see why did I introduce this coset algebras, this coset of the small hook W and W superalgebras, because they are Y algebras where one of the labels is 0. So this means that the Y algebras, recall that the C psi was the coset by the affine GLM subalgebra of a hook type W algebra of SLN plus M, and the D psi is the GLM coset of a hook type W superalgebra of the Lie superalgebra SLN/M. And so essentially these cosets are the Y algebras up to tensoring with a single free boson. Okay, let me, so if we, in this picture, I said the associated vertex algebra is not the tensor product of these 3 Y algebra, but an extension of this. And there's a precise formulation of this. So the representation theory of a category of modules is hopefully a rigid braided tensor category. And as long as you can prove that this is actually true, then you have a very nice theory, namely that extending the tensor product of 2 VOAs is equivalent to having an equivalence of tensor subcategories of these 2 VOAs. You can extend these 2 VOAs if and only if they have a subcategory that is braid reversed equivalent. This braid reversed means that you can pair the operators such that they can that the corresponding OPE of the is local. So categorical, I mean the locality of the operator product algebra of the VOAs and this extension in these extensions is on the categorical level the same as having a braid reversed equivalence. So what it means sloppily speaking, and that's a good way to think about it, 2 VOAs can be extended to a larger structure, to a larger VOA, if and only if they share a common subcategory. And this is exactly what this picture will say here. This Y algebra and this Y algebra, they share the corresponding Kashtalushtik L/M category. Okay, and this picture of gluing vertex algebras is very, very key in the corner VOA or webs of VOA construction, and also actually in the four-manifold story. I now want to spend the rest of the talk talking about two conjectures coming from physics and what we have to say about those. So the first conjecture is the triality conjecture of Miroslav and Davide, which in a similar form has been conjectured before by Garbadil and Gopakuma. And it says that if I simultaneously permute the indexes, the NLM of the Y algebra, and also transform the coupling constant psi in an appropriate way, then I get an isomorphism of Y algebras. That means they have an S3 symmetry somehow. This is from the physics setup obvious, right? Of course, if I have my Y, I can rotate it, I still have a Y. And the question is, does the coupling change under these procedures? And this is encoded in these formulas. So one key conjecture, one should say, is whether one, is this actually true for the corresponding VOAs? I mean, can we confirm the VOA predict and the physics prediction? Can we prove this prediction? And Andy Linshaw and myself, we have a theorem that this is indeed true if at least one of the labels is 0. So if all labels are non-zero, then we can't do the proof because one needs to know too much about representation theory of Lie superalgebras. So this is too complicated for the moment for us. But this theorem says there's a triality of cosets of small hook type W-algebras. That means there's a triality of Y-algebras. And what it says is here this coset of the W superalgebra is isomorphic to this coset of the W algebra, where the shifted levels are inverse to each other. So where do we know this? An isomorphism of W algebras where shifted levels are inverse to each other. This is Fagan-Frankel duality of a principal W algebras. And indeed, a special case of the statement is the original Fagan-Frankel duality. So this first isomorphism is a large generalization of the well-known Fagan-Frankel duality, while the second one, or better, this one, the inverses of the shifted levels add up to 1. So this isomorphism actually is a large generalization of the coset realization of W algebras. We will see this a little bit more explicit in the coming slides. Okay, so now you can say, so what, we confirmed a statement from physics. The physics conjecture was very clear. That means there was very few doubt that that conjecture was true. Nonetheless, I mean, of course, it's always important to prove a conjecture, but also we developed quite a few new technology in order to prove this. So because we had to prove quite a few properties of these cosets. First of all, we had to show that these are simple vertex algebras for generic parameter. And the way we did this, we studied a large level, a large psi limit, which one usually does in order to get some Poisson vertex algebra, but we did a slightly different limit so that we got what we call a generalized free field algebra. And then from looking at this generalized free field algebra, or this limit more generally, we were able to prove the simplicity statement, and also that what are the generating fields of what type are these W algebras. And then the key step is, so my collaborator Andy Linshaw, he proved that there exists a unique two-parameter VOA of type 2, 3, 4 up to infinity. So it's called the W infinity algebra that has been discussed a lot over the last 30 years in physics. And we can prove that our cosets are one-parameter quotients of this one. And we can explicitly determine which quotients these are. So there has been this conjecture by Miroslav and Davide. We can prove it when one of the labels is 0. And then there are a few more conjectures by these people together with Prochaska. Namely, they also expected that this Y algebra is actually a quotient of this W infinity algebra. And they also predicted what kind of, how to characterize this one parameter subfamily nicely. There's a very nice parameterization for it. And they also predicted what are the strong generators of these Y algebras. And all these things we can prove if at least one of the labels is 0. So this is the first thing I wanted to report on. Now we have developed some new technology on how to prove these VOA conjectures coming from 4-dimensional physics. But now, having had this observation, it's of course nice that you can say that a certain coset VOAs are isomorphic. But it's kind of nicer if you, I mean, it's of course nicer if you have a more direct relation. And I think it's very instructive to think about these new VOAs that appear as somehow coming from VOAs that are somehow generalizations of Peter Weil theorem for compact Lie groups. So Peter Weil theorem just tells us that the space of function on a compact Lie group is the direct sum of all irreducible representations times their duals. And now let me simply tell you what the generalization is. Now, instead of taking the finite dimensional representations, I take now 2 affine vertex algebras and take the corresponding induced modules, the Weil modules. And then, and then of course, so this means instead of taking the space of functions on the compact Lie group, I take a corresponding vertex algebra object. That means it's the direct sum of the Weil modules. I sometimes have to add some kind of dummy VOA to make it local. This is not too important. But then I can, of course, also do the quantum Hamiltonian reduction on either the first factor or on both factors. So that, and this is a conjecture that appeared in my work with Davide, where we simply, where we observed that these types of VOAs should exist, and indeed one can prove in many cases that these VOAs do exist. For example, if I take n equals 2, then this very first algebra is the affine vertex superalgebra of D21 alpha of this very exceptionally superalgebra at level 1. And now one observation is that this triality of Davide and Miroslav is related to these vertex algebras that are tailored after Peter Weil. And namely, we have this conjecture. If you take this large extension of 2 affine VOAs of type SLN, you perform the hook type reduction on one of the factors, and then this still has an affine GLM subalgebra, and you take the corresponding coset, then you get a W superalgebra that appeared in the triality. And similarly, if you take one W algebra in our triality, you tensor it with one of these Peter Weil type VOA extension, and you take the relative semi-infinite Lie algebra cohomology, you get the third type of W superalgebra that is involved in our triality. So it seems that this triality of coset algebras holds, but there's a much nicer structure namely these A of SLN psi algebras, which are direct sums over all our dominant weights and the corresponding Y modules diagonally paired, and then just applied some standard construction to it. And recall that the coset construction can also be phrased in terms of this Lie algebra cohomology. So I could also have written this first conjecture in terms of this relative semi-infinite Lie algebra cohomology. And Andy and I, we were able to confirm the first conjecture on the level of characters, which was actually enormously difficult because you had to understand how certain multivariable meromorphic Jacobi forms decompose, and they were not of, and so that was actually quite difficult. And we didn't try, yeah, thank you. And we didn't try to prove the character statement for the second one. Okay, I want to spend the last very few minutes to talk about the second W-algebra observation we have. And this gives so let's first recall that vertex algebras are also nicely connected to geometry via the AGT correspondence. And the main theorem I have in mind here is the theorem by Schiffman and Bassaro that says that the equivariant cohomology of the moduli space of torsion-free coherent sheaves on CP2 equipped with some framing at infinity concerns has a W-algebra action. And nowadays, one is again interested in large generalizations of this. And the best theorem at the moment is due to Rabchak, Soibelman, Young, and Zhao, which is a similar statement, namely that W-algebras called Wn, M, L algebras act on these cohomologies, and the conjecture is that these Wn, M, L algebras are the same as the Y algebras of David and Miroslav. And if you do this connection to geometry, the W-algebras are realized as some kernels of screening operators, which is one way one usually views W-algebras. And so one has, for this new type of W-algebras, one has also to prove the screening realization, which involves understanding screening realizations of W superalgebras, which needs to be developed. So we were able to do this for the very first case. And now the idea of Sergey and Boris is that also the equivariant cohomology of this modular space of G instance on a form manifold has a VOA action, and they observed and these form manifolds are labeled by VOAs, the boundary components by categories. And the gluing of form manifolds is again corresponds to this VOA extension problem I presented before. Now, what I found extremely striking is the blow-up observation from them. So what they did is they took a form manifold, they removed a small four-ball, and did the same with CP2 with reverse orientation and glued them together on the common S3. Now, to each form manifold, they associate a vertex algebra. So that means they would like to know what is the vertex algebra associated to this glued manifold. And the claim of them is that this is a very simple construction. It's just the tensor product of the original vertex algebra, the vertex algebra associated to the original form manifold, tensored with some object called the urod. So urod is Russian and is not a very polite word, but it's actually a very nice object. And the underlying theorem for the urod, so all I will want to do for the last 3 minutes is to present, show you that this statement is very nicely reflected in a property of the quantum Hamiltonian functor. I mean, this statement I like to rephrase as this theorem, saying that the quantum Hamiltonian reduction functor commutes with tensoring with integral representations. So this means I take an affine VOA at level k, an integral one at level n, then I can take the tensor product and I have the diagonal reduction at level k plus n, or the reduction on the very first factor. Our theorem is that the answers are the same. However, the conformal vector on this integral representation is somehow unusual. And why is this interesting? So the OROT, first of all, is nothing but the integral representation at level 1. Well, this is interesting because the coset realization of principal W-algebras says that if I take my affine VOA tensor with the integrable VOA at level 1, it's an extension of the affine VOA at level k times the principal W-algebra. And now I can apply the theorem that the quantum Hamiltonian reduction functor commutes with integral representation to this theorem. This means I replace this factor by the corresponding W-algebra, and I replace here the highest weight modules of the affine vertex algebra by the corresponding W-algebra module, and the same type of statement holds. So this is a very surprising statement because it tells you W-algebra of type F prime times L1G times this very simple OROT VOA contains an action of the W-algebra at level shifted by 1, hence the name translation, and the commutant is a principal W-algebra. And this theorem should be viewed as a VOA version of the prediction that the gluing of a 4-manifold on a CP2 bar is nothing but on the VOA level taking the tensor product with a very simple VOA, namely the OROT. Okay, I'm sorry that I was at the end a little bit fast. Let me summarize. So vertex algebras, especially W-algebras, appear as meaningful invariants of 4-dimensional gauge theories. And there have been 2 predictions that I found particularly interesting, namely the triality, that means the certain cosets of certain W-algebras enjoy a triality of isomorphisms. And another prediction is that somehow there exists a mysterious VOA, which is nothing but the affine VOA at level 1, so that if I tensor a W-algebra with it, I get an extension of 2 W-algebras. And we were able to prove these 2 types of predictions coming from physics. And it actually turns out that these 2 observations seem just to be the tip of the iceberg of many, many nice things to come. So for example, we are at the moment looking at much more miraculous properties of the quantum Hamiltonian reduction functor, which probably will have many future nice applications. Okay, yeah, let me finish here. Thank you very much for your attention.
Thank you very much, Thomas, for this nice talk. I'm just going to unmute the participants so they can give you a round of applause. Okay, so now we've got some time for questions. If you have any questions, please just raise your hands on the Zoom button, or if you're unsure how to do this, just write into the chat. We've got a question from Faye Key. Please just unmute yourself, Faye, and go ahead. Faye, I think you're unmuted. Okay, maybe there's just a technical problem. Something's wrong with his microphone. Okay, do you want to just type in your question and then I can read it out and Thomas can answer it? Maybe while Faye's doing this, I can just ask a question, Thomas. So the way I understood it so far, you are taking, I mean, you're taking the physics conjectures and then trying you get new predictions for VOAs, which, as you say, difficult sometimes to prove because of the representation theory. Is there anything you can say going the other way? So having developed some of the machinery you have, are you led to any new conjectures you might pose for the physics? You're just muted.
Can you hear me?
Yeah, I can hear you now.
Yeah, this is the nice thing. Yeah, indeed. I have two conjectures which I really like, and I haven't seen them in physics, and they are somehow natural in generalizations of this theorem that I had, that the quantum Hamiltonian reduction functor commutes with tensor and with integral representations. So let me tell you how do you put physics aside, come up with this conjecture. Well, if you for some reason look at these two reductions, you will observe that the supercharacters of the complexes coincide. And moreover, you have a no-ghost theorem, which implies that the supercharacter is actually the character of the reduction. So this means that this theorem is not coming from nowhere. It comes from the observation that this is already on the level of characters and equality. And having that in mind, you can ask yourself, can I set up more complexes which have the property that their characters coincide? And of course, they also should share more common properties. And for example, Davide and Miroslav have this YLMN algebras where all indices are non-zero, and they correspond to other reductions of Lie superalgebras that are too complicated for us. But for example, what I can prove, I just have to write it up, is that the corresponding W-algebra, whose coset is YLMNN, has the property that there exists a new type of reduction that gives the W-algebra where every index is reduced by 1. So this means somehow, if you look at it from the physics side, somehow you can reduce the rank of the Lie groups on the interfaces simultaneously by 1, or then actually by any integer. And this seems to be interesting. And then there's a super powerful conjecture, which I call the small reduction conjecture, which so if I take a big Lie algebra G, and I take a nilpotent element that is also nilpotent in a subalgebra, then I can view my big vertex algebra as a vertex algebra of the big type, or as a module for the smaller one. And I can take the two corresponding quantum Hamiltonian reductions. If you look at the complexes, you observe that the complexes differ by a free field algebra, by some ghosts. The statement is that the same is true for the reduction, for these two different reductions. And if that is true, then one gets a mathematical framework to describe the gluing of the Y-algebras very nicely. So this is a very, to me at least, a very important conjecture. Yeah.
Okay, thanks. So we'll have to keep an eye out then for the future work. So they managed to write their question. I'm just going to read it out, and maybe you can answer it directly. So, is there anything known about intertwining operators among representations?
Of these Y-algebras, I assume now?
I assume so. Yes, let's assume this. Maybe they can correct if...
Yeah, not much, no. This is unfortunately not. So the main thing we would like to prove is that the intertwining operators between W-algebra modules give us a rigid braided tensor category. And in order to prove this, one needs to verify certain finiteness conditions, which we only managed to do for the Virasoro case, for the W-algebra of SL2 so far. So, I mean, this is a totally natural question, and one definitely should study it a lot. unfortunately, it's somehow difficult.
Thanks. So phase writing, there is a C2 cofiniteness. C2 cofiniteness is a problem.
Yes, I mean, these algebras are very far away from being C2 cofinite. So this is I mean, first of all, it's not easy to show C2. So C2 cofiniteness would imply the tensor category statements. That's why it's interesting. But C2 cofiniteness also implies that there are only finitely many simple modules, inequivalent simple modules, which usually fails for these VOAs.
Great. Thanks. So then there's another question from Yifan Wang. Yifan, please just unmute yourself.
Hello.
Hi, we can hear you.
Oh, okay. So I have a question about your last slide, point 5. Can you go back to that slide?
Yes.
Right. So you mentioned there's this relation between W-algebras and Toric Clapeyron threefold.
Yes.
So my question is, can you use relations between various W-algebras to try to understand string theory dualities?
And to understand.
For example, there's for example, by doing two-duality, there's a brane realization of the Toric Clapeyron threefold.
Yeah.
From PQ5 branes. Is there an intrinsic W-algebra construction there? And can you use that, the relation between that W-algebra and this W-algebra you identify directly from the Toric Clapeyron threefold to understand dualities in string theory?
Yeah, that's a good question. I don't know. At the moment, all I know is, so I think if you give me a Toric variety, then and you give me time to sit down, then I can probably tell you what's the corresponding VOA. But then,
right,
and then of course one can think about, I mean, look at what we know about this VOA and see what kind of what the isomorphisms that we know about these W-algebras tell us.
Right.
But I can't say anything explicit at the moment.
I see. Thank you.
But it's a very nice game already, how to take your favorite Toric threefold, write down the corresponding PQ web, and then you know how to, I mean, then choose your ranks, choose your gauge groups on the interfaces, and then you already have a way to write down the corresponding VOA. But yeah, then how to go on is I don't know.
Sorry, just a follow-up question. For non-Toric Clapeyron, this is not possible because you don't have the PQ web description?
The combinatorics here is tailored after the PQ web. So this means for this type, it's just Toric Clapeyron. But who knows, maybe there's something beyond PQ webs for the UAs.
But is there like an underlying, I mean, a more general principle that tells you when I have a Clapeyron threefold singularity, Clapeyron threefold variety, I should expect a W-algebra? A more fundamental perspective. I mean, whether this W-algebra can be described in the way that you mentioned, depending on whether the Clapeyron has a Toric description or not. Is there a more fundamental principle tells you that you have to, I mean, there is a W-algebra lurking?
Yeah, I don't know.
Okay.
Sorry.
Right. So any other questions? There's another question from Mikola Dedushenko. Please just unmute yourself.
Hi. I just something related to previous questions. What are the challenges when the PQ web has loops? Because I think Miroslav and co-authors only consider trees, as far as I remember.
Yes. Loops would just, so the way you think about it is these Y-algebras, they have three hands, they have three categories. And if you do two Y-algebras, you glue them along one category, but you can, of course, if a second one also corresponds, you can also glue along that one and you get a loop. So there's no big problem in that, no. yeah, loops are they fit well into this framework. I mean, yeah. So mathematically, it's hidden in the statement that these three categories that this Y algebra has, they centralize each other. This means if I do one gluing, then the extended VOA still has this type of category as a category of modules. And that means I can also then glue along a second category and get a loop. Yeah. Okay, if you want, I can explain that in private, maybe in more detail. You don't seem happy.
Nicola, you're just muted, but yeah, maybe given the time, it's best to leave this to private discussion. There's also a comment on the previous question, but yeah, I mean, maybe since we just have only a couple of minutes left before the next talk, it's best to just leave it at this. Thanks again, Thomas, for the interesting talk and for this discussion. And yeah, then we can maybe set up the next speaker. Thanks, Thomas.
Thank you.
Let's just see. Well, okay. Jeff, are you around?
Yeah.
Great. Could you give Pavel?
Pavel, I've given you co-host.
Super. Just happened.
Okay, thanks. Can you hear me?
Yep.
Yep. Pavel, you may want to just try and share your screen to make sure that all works.
Yeah. Okay.
Very good. So you can also go into full screen mode. That might be easier to view.
Is this okay?
Currently, it's still black for me. Maybe just press something.
No.
No, the screen is now blank for me. Yeah, now I can see it again.
So let me just share the whole screen.
There we go.
Is it okay?
Yep.
Yeah, now it's good. All right, great. So we'll just start in like half a minute. Okay, so we'll now move on to our next speaker. Maybe just before we get there, just a quick reminder, if you've just joined, please keep yourself muted during the talk. We'll leave questions till the end of the talk. There's 20 minutes set aside after the 40-minute talk for questions. Please raise your hand using the Zoom functions. If you click on participants, you should see a row of buttons, including raise hand. Then I will pick you out in the question session in order. If for some reason you can't find that, just message in the chat your question, and I'll make sure it's asked at the end. Okay, so with that, it's a pleasure to introduce the next speaker, Pavel Putov, who will tell us about supergroup Chern-Simons theory, Q-series, and resurgence.
Okay, so, thank you for the introduction, and thank you for inviting me to give a talk. So my talk will be based on our work in progress with Francesca Ferrara. And so in my talk, I will consider a certain family of Q series with integer coefficients, which are labeled by supergroups of type SLMN and associated to a three manifold. And I will consider three manifolds, compact-oriented three manifolds of a particular class. And conjecturally, this Q series has the following physics interpretation. So up to possibly some overall universal normalization, conjecturally they should be equal to a trace of a Hilbert space of a certain quantum system, or in other words, to a Q-flavored index of the following system of M5 branes. So we start with M theory on a total space of a Lagrangian bundle over a three manifold, and we take it a product with C squared, which we actually want to compute with Taub-Knot metric times S1, and we want to put n copies of M5 brane on M3 times C times origin of the other C, and M copies of M5 branes on M3 times origin times the other C. And this L0 inserted in a trace over the Hilbert space is a generator of rotation of the C of both C's in opposite directions. And as I will briefly review this system by this M theory set up by duality is related to supergroup Chern-Simons, supergroup SAM and Chern-Simons theory on M3. And I will consider various examples and also some properties of this Q series, in particular their resurgence properties. And I will also make a statement. Also, it's a conjecture. How these Q series are related to a certain known invariance, known quantum invariance of three manifolds, and these are invariants of a type considered by Constantino, Gear, and Potirot-Miron. And so these are not the usual quantum invariants associated to model tensor categories, but they are rather associated to a certain non-simple category of representations. In our case, it's a representation of a certain what is called unrolled version of quantum SLM-MN with a modified trace, and we want to take Q to attribute of unity. Actually, I will focus mainly on the case when m equals 2 and n equals 1, the simplest non-trivial example. And this was worked relatively recently in a work by Ha. This application of this more general construction. And so let me mention, so in a sense, this is a generalization of a work already done for the case of ordinary Lie groups SUN, and also to some extent to U1 bar 1. So for SUN case is just when we only have n and 5 branes, but we don't have anything here. Okay. So before proceeding to doing short review of supergroup Chern-Simons and its brane realization, let me first review the brane realization of the ordinary SUN Chern-Simons. So this can be realized by considering a system of n D3 branes supported on three manifolds times half line, and they end at a NS5 brane. And so there is the work volume here living on these D3 branes is a maximal supersonic super Young-Mills with a certain coupling constant tau. And at the infinity here, we want to impose conditions that the gauge fields approach a certain flat connection. And then there is a statement that made by Witten in particular, that the Barchin function of such system. So we also need to perform a topological twist around M3, along M3. So the statement that the Barchin function of the system realizes a certain analytic continuation version of Chern-Simons theory, where the Young-Mills coupling is defined with the level, analytic continued level, and this Barchin function realizes the path integral over a certain contour known as Lefschetz symbol associated to this particular flat connection. But then one can do a S-duality in type 2 base theory to replace this brane to D5 brane, and then, but this actually will in general will transform non-trivially this conditions on the field, boundary conditions at infinity. And then first one can make T-duality to type 2a. So instead of D3 branes, we will have D4 branes on M3 times half line times this one, and they will end on D6 brane. And then the system can be lifted to M0, where now the half line is lifted to a cigar, and so the cigar can be sort of a circle vibration over plus, with the circle being a M0 circle. And yeah, so this, to be precise, this cigar is a cigar inside a Taub knot space. And so in this setup, the Q is exponentiated equivariant parameter corresponding to rotation of this cigar when we go around this one. And Q is related to continuous Chern-Simons coupling by the following relation. Now, this can be generalized to a supergroup version. It's just that we don't have only D3 branes on one side, we also put D3 branes on the other side. And essentially we can make the same sequence of dualities, and we end up instead in M0, instead we have N M5 branes wrapping one cigar and M M5 branes wrapping the other cigars, and they cigar, like you can imagine, because they touch here. And but they actually, they actually intersect transversely in a Taub knot space as two copies. If we answer Taub knot as C2, they just C one copy of C and the other is wraps another copy. And okay, let me also mention as a kind of part of motivation that this kind of supergroup Chern-Simons is a kind of physically important object. This also appears, for example, in the sort of relation to a BGM sphere on a 3-sphere. So probably the most well kind of understood version is for when the group is U1 bar 1, and as was shown in particular by Razonsky-Salur, this Chern-Simons, the corresponding partition function of this Chern-Simons theory is equal, can be identified with the Rademacher-Torayev torsion on a 3-manifold. And in turn, the Rademacher-Torayev torsion can be identified with the Lebesgue-Witten invariance, as was showed by McTaubes. Here, I mean 3-dimensional Lebesgue-Witten invariance. And what is nice about this case, here it is known both for invariance of 3-manifolds and nodes, corresponding invariance nodes, it's known how to categorize this environment. In particular, one can write the following table. So the corresponding invariance of nodes here is the Alexander polynomial, and its codification is not for homology. And similarly, as the codification for 3-manifold invariance is monopole for homology or equivalently Hilbert for homology. And it also actually can be extended to invariance of 4-manifolds, which are 4-dimensional Lebesgue-Witten invariants. And so in a sense that this, so roughly this homology can be stood as a Hilbert space of the corresponding 4-dimensional QFT on a 3-manifold. So kind of the wish, it would be to have this, to fill this table also for SU2 group, for which we know some parts. So we know what is the invariance of for nodes. It's a John polynomial, and it's known as codifications Havanov-Razonsky homology, and we know the invariance of 3-manifolds. So we don't actually have to derive invariance, but it's not. I mean, there are some physics proposals about what should be here, but they're not. Yeah, they're not mathematically so far well defined, and even on computational level, it's not clear how to, in general, do this. I mean, how to calculate them, even from physics point of view. So in a sense, this is as a part of motivation, one can try to consider the simplest supergroup, which includes both cases, which unify, in a sense, unifies them. And so the hope that maybe this is kind of can bridge these two cases. This is just a part of motivation. So I will be interested in considering the following class of 3-manifolds, which are called Plum, usually referred as Plum manifolds. So they can be combinatorially described by a plumbing graph. This will be a graph for which each vertex has an integer label, AI here, and the corresponding manifold can be understood as a Tensor on a link associated to this graph in the following simple way. So for each node, we consider a node which is for which it's actually framed and not for which the framing is given by specified by the corresponding integer number. And these unknowns, a bunch of unknowns, they're linked in a way as this graph. So for each edge means that the unknowns are linked in the simplest possible way. And so let me briefly remind you what is a dense surgery. So dense surgery is so for each link component we cut out its tubular neighborhood. So we get something with a torus boundary, and then for each of these torus boundary, to each of these torus boundary, we glue another copy of the solid torus using the following SL to D transformation, where AI is specified by this integer framing numbers. And so in the follows, I will denote by L the number of vertices in this plumbing graph. And so the important quantity associated to this graph is L by L linking matrix. So it's just equal to 1 if two vertices are connected, and it's equal for diagonal elements, they're just given by the framing numbers, integer framing numbers, and 0 is C0 as always. And in particular, then the first homology group of this three-manifold obtained by this surgery can be identified with the kernel of this matrix M. And in what follows, actually, I will consider only 3 graphs, and moreover, I will assume that this is the manifold is a rational homology sphere, so the first Betty number is 0, and in particular, this means that M is invertible over rational numbers. Okay, so let me before going to Q series associated to manifolds and supergroups, let me briefly review the Q series associated to ordinary groups and the 3 manifolds of a type of plumbing graph. So they were considered in a paper by Gukov, Pei, Wafa, and myself. And there was given the following formula in terms of this plumbing data, what would be this the head series associated to an ordinary algebra. And so they're given by the following, one can write the following integral formula. And so for each vertex, there is one introduces a single variable zi, and then the integrand contains the following rational function of these zi's, and then we multiply by theta function associated to a quadratic form, which is 2 minus 2m. M is a linking number, is a linking matrix. So in particular, this is and the integral. So of course, in principle, there's some singularity, and one has to choose how to avoid the singularity in this contour. And here, one can make what is called principal value prescription, which means we take an average of all possibilities. So this is readily well defined if M, for example, is negative definite. So this theta function is a convergent. But in principle, this can be generalized as was generalized for the case of what is called weakly negative definite. And also, let me know. So these Z-hats. So in general, they have labels. So it's not a single Q series. It's a family of Q series. So in the brain pictures, they're associated to some choices of boundary conditions. So they, as was clarified in the paper by Gukov and Manolev, they actually more naturally labeled by a set of spin C structures on the 3 manifolds, which can be identified with the cokernel of 2m. With the elements of cokernel of 2m, so this define a certain parity condition. In any case, so this was a brief review. So what I'm actually interested in constructing something similar for the case of supergroup, in particular SU2 bar 1. And so in this case, the generalization is the following. And so first of all, let me mention, so even though the kind of, as you will see, the case of supergroups will have some qualitative differences from the case of ordinary link groups. So so in this, for the case of SL2 bar 1, we want to associate a pair of complex variables for each vertex, And so we want to integrate over them over some contour. And so we insert a certain rational function where degree of I is a degree of a vertex. This vertex has a degree 3, this vertex has degree 1, and this has degree 2. And so formally, this can be written later. So we also insert in the integral as a following kind of indefinite theta function associated to M inverse in this way, in this particular way. But of course, this is unlike in the case of ordinary algebra. This is never convergent. So one cannot define it in this way in any case. And so what we actually should interpret this is that this formula is that what we want to do, we want to make some choice of contour, and corresponding to the choice of contour, we make an expansion of this rational function in certain chamber, and then we just take this integral means that we just take a constant term of this thing. But of course, not for even after that kind of prescription, not for all choices of contours. This is will give you well-defined Q series. So there's a question like what is the conditions of the choice of contour of gamma? So this actually produces well-defined Q series, and if there is such a choice of contour, is it unique? So one can give a rather technical but very specific kind of algorithmic answer to this question, which I don't want to go into too much details. But so one can formulate as a condition on the existence of contour that this minus M inverse matrix is what can be called weakly copositive. And so this is a kind of a bit different condition to this weakly negativity condition, which we had for the ordinary algebras. And the good news is that if if such contour exists, there are actually only two choices, and they give the same result. So this is uniquely defined. It gives a unique Q series. And so this is a Q series with integer coefficients up to and integer powers up to some probably overall shift, overall rational power of Q, which is invariantly can be formulated as a linking pairing between these labels B and C. So the labels B and C, from the point of view of this linking matrix, they live in co-kernel, but more invariantly, as they can be the element of the first homology group of a three-manifold with integer coefficients. So we define this Q series in terms of a plumbing graph, but in principle, it's known that the plumbing graphs can realize the different plumbing graphs can realize the same three-manifold. Well, the different plumbing graph can realize homomorphic three-manifold. And so if this is something actually, if it's a topological invariant, then we should check that this the result is not independent, and it is known that what is the kind of moves on the plumbing graphs can be made so that two different plumbings realizing homomorphic manifold it is known the set of moves which relates the two plumbing graphs realizing the same homomorphic manifold. And one can check that this formula, although it's explicitly depends on the plumbing data, is actually gives you an invariant. And moreover, this condition on M is also preserved under this moves. Okay, let me give you some examples just to get a feeling what kind of Q series one obtains in this ways. And so, okay, the simplest example you can imagine is a three-sphere. So there is the first homology is 0. So there is actually there is only a single label. So in general, I remind you, so they label by pairs of H1. So just a single Q series, and it is something actually familiar. This is what is known as Lambert series, the series of Lambert type, and this is a generating function of the number of divisors of M. And there's a generalization for length spaces LP1. So in this case, this now we have H1 is isomorphic to ZP, and so the pair of elements of the ZP, the Z hats turn out to be generating functions for the certain numbers, numbers which answer a question for this counting problem. So it's a count pairs R and S satisfying, so the product is M, and they're equal to B and C respectively modulo P. So let me make a remark. So that this is already for the level on this level of simple manifolds like length spaces. This is very different from the Z hats for SLN, which were just Laurent polynomials in Q1 of P. But here, this is some full-fledged and non-trivial Q series. And also one can notice something similar, which is a bit of kind of a puzzle or maybe coincidence. These numbers actually they coincide with early characteristic of moduli space of M SO3 instantons on LP1, the same LP1 as we had here, times R propagating between flat connections labeled by B plus minus C, which are computed by Austin in 19. Okay, so let me consider something more involved. So consider, for example, Lambert manifolds with 3 exceptional fibers. So in terms of plumbing, they can always be realized by a star-shaped graph with 3 rays, something like this. And one can argue that in this case, this Q series, they can always be given as a linear combination of the series of the following form for various for some parameters alpha, beta, gamma, A, and B. And so, for example, if you the Q calculation from Poincare homology sphere, which corresponds to this plumbing graph, it gives you something like this. And again, so if you want to compare it to the case of SL2, in that case, something was the Q series was a bit of a different form. So it was a kind of the powers was rather sparse, and the signs were alternating, and this was what is known as Q series of class of false model forms. Sorry, false theta function. Okay, now, yeah, so I want to address some properties, some analytic properties of this Q series. So, for technical assumption, let me assume that H1 is 0, so there will be just a single Z hat, and consider its expansion in terms of H bar, which is logarithm minus logarithm of Q, or proportional to tau equivalently. So in general, there will be some singular part plus the sum of positive powers of H bar. So let me know that M do not necessarily run over integers, they can also run over half integers in general. And then we can define a Borel transform as the following series in Xi, where we divide it by coefficient by gamma divided by n+1. And the general kind of knowledge tells us that if this Z hat, for which we consider simple expansion, were originated from some sort of path integral of analytic continuum Chern-Simons theory, then we expect a certain properties of this, certain nice properties of this Borel transform. So even these are asymptotic expansions in general. This should be this series, Borel transform series, should have a finite radius convergence, and moreover, one should be able to analytically continue them beyond this radius of convergence, and the possible singularities that can appear once one does this analytic continuation should be positioned at 4 pi squared times S, where S modulo 1 should be the value of a Chern-Simons invariant of flat connections on a 3 manifold. So I'm going to ask the question: is it the case for SL21? At least in some simple cases. So okay, the simplest case would be S3. And here one can see that this Lambert series, which the simple expression of Lambert series is known. And it's, well, it's simple, but it's still non-trivial. So this is not a convergent expansion. This is a asymptotic expansion. And it's rather easy to analyze this Borel transform and see that the singularities are positioned at 4 pi squared times S, where S is integer. which is model 1 is just 0. And this is okay because, well, the only flat connection is a trivial flat connection on S3, and this is just the lifts of the same trivial flat connection. Again, this is quite different for the case of SLN, where this for SO3, this Q series was actually, like this was, as I mentioned, it was Laurent polynomial in Q, and this was actually entire function in H bar. And there was no non-trivial resurgence here. And so one can also make the same analysis for the manifold with 3 exceptional fibers using this property that, yeah, as I mentioned, that they can be, the Q series can be realized as a linear combination of Q series of the following type. So it's enough, it's sufficient to first do a general analysis for this type of co-series for general alpha, beta, gamma, A, and B. And okay, this is not something unlike the Lambert series. This is not something which you can find in the literature, at least we couldn't. And so one has to do some work, and one can do the analysis using Euler-Maclaurin summation formula. And one can find that this has single, the Barrel transform, analyze the asymptotics of the coefficients of the asymptotic expansion of this Q series. One can deduce that the Barrel transform has singularities at these points, 4 pi squared s, where s is either of this form or this form, where k is integer. So if you try to plug in these results for example, Poincare homology sphere, so at least naively there will be a lot of singularities from all of this contribution of all different f's in the sum in the linear combination. But one can show that actually there's some non-trivial constellations. The only so many of these singularities are actually fake; they cancel out, and what is left is just singularities when s is 0, 1 divided by 120, and 49 divided by 120, model 1. And this is they corresponds to value which is functional of SU2 flat connection, where SU2 can be a subgroup. SU2 is a subgroup of SU21. Okay, so now I want to to say something about relation to certain quantum invariants known in mathematics literature associated to a quantum version of quantum SL21. So first, let me. It is known that if one tries to use the standard recursive derived construction to the topological invariants for topological invariants for quantum SL21, this actually leads to trivial invariants, in particular because the quantum dimension will vanish. So one has to do something different, and in particular, what one can do is apply is a kind of use a notion instead of modified trace, which makes this quantum dimension, in particular, makes quantum dimension non-trivial, and use the general construction of Constantino, Geer, and Potiron-Miron applied to the case, which is applied to. So this is a general construction which one can apply to certain non-single categories. In this case, this non-single category is a category of representations satisfying certain conditions of what is called unrolled version of quantum SL21. When we take Q to, well, there is some subtlety with normalization, but we take Q such that Q square root of Q is an odd root of unity. And so the particular case of this corresponding to SL21 was worked out by Ha. And so in a sense, in a roughly sense, these invariants can be assumed as a normalized version of the usual Chern-Simons partition function, which makes this non-trivial, makes invariant non-trivial. At the end of the day, there is a certain formula for an invariant of the following form. It's actually not invariant of just of 3 manifolds. First, of course, it depends on the choice of k, of the integer k, but it's also not just invariant of 3 manifolds, but 3 manifolds colored by omega, where omega is the element of the certain set. So so you start with the first homology, first cohomology over 3 manifolds with coefficient being c mod z times c mod z, but you have to exclude some subsets, some subgroups. And so in particular, you want to exclude a subgroup where the first component is actually valid in the first homology with half integer coefficients, and you want to do the same for the second component, and you also want to do the same for the diagonal. Anyway, this is just some technical details, but so how roughly this omega, this weight omega, this color omega enters in the construction. So this can be understood as follows. So in general, these representations, which one considers here, they have weights in C times C, labeled by two complex numbers. And what we do when we do for each, as in the usual kind of similar to the usual Rashid-Kim-Turaev construction, when we do a surgery, we need to sum over some representations for each link component. And what we do here, so for if you take a particular link component, we want to make sum only over representations such that the weight equals to weights modulo z times z, they equal to the value of this omega evaluated on a meridian surrounding this link component. Okay. Again, at the end of the day, there is some combinatorial formula for this invariant which allows you to calculate this. So one can make the following. So we want to make the following conjecture, so that when again M3 is a rational homology sphere, this Q series Z hat are related to this non-simple quantum invariance by the following formula. So it may be look a bit complicated, but essentially it's just what we want to do. We want to take a certain linear combination of the Z hats, and we want to take Q the limit when Q goes to a root of unity. And there will be some universal overall coefficients involving Meister torsion. And okay, so let me make some comments here. So before you may notice that before actually my Z hats for SL21 were labeled by a pair of elements of H1, but here instead actually I want for them to be labeled by the elements of H1 of the first cohomology with coefficient being C mod Z instead. And this is possible because for rational homology, first cohomology group with in C mod Z is actually can be identified with the first cohomology with coefficient in Q. But this in turn can be actually isomorphic. There is a particular choice for isomorphism of this group to H1, the first homology group with integer coefficient, by using the linking pairing, which is non-degenerate pairing on the first homology to Q mod Z. So in this isomorphism, one can instead label the hats by elements of first cohomology with coefficient in C mod Z. And then roughly this formula can be stood that, so first we do essentially Fourier transform with respect to this B and C, pair of B and C when we pass the variables Q and beta, the dual variables Q and beta. And then we do again Fourier transform with respect to beta and gamma, but we also insert this quadratic term depending on K or level and the linking pair between beta and gamma. Okay, so let me mention some kind of open questions and possible future directions. So as you also probably could notice that in all simple examples, as all coefficients except possibly the constant term turn out to be positive. So first of all, is it true more generally? It's actually not so easy to answer because like to generate, it's not obvious why this should be true. At least we don't know explanations for it. But it's actually hard to go into kind of complicated examples to calculate many terms to check it kind of experimentally. It becomes a bit time consuming. And first and the second, of course, it's natural to ask if there is some categorification of this Q series. Similar, for example, to E1 bar 1 case. So of course there is a physics kind of physics prediction, some sort of BPS spectrum prediction for what should be categorification. But again, maybe since in this case it's well understood for U1 bar 1, and this is a subgroup here of SU2 bar 1, one might come up with some sort of better understanding, some better mathematical understanding of maybe some combinatorial definition of this codification. And also, in principle, one can expect the other point is one can expect some relation when the supergroup is PSL and bar n. One can expect a certain relation between instant on counting on M3 times R of this Q series and some generative function with some Fourier characteristic of instantons here. This is because, so in this case, we have n branes on one side of d phi brane and the same number of branes, d3 branes on the other side. And there is a phase, physically, there is a phase one can separate this d phi brane and then this d3 branes, they become just supported on this M3 times R. And of course, it's obvious, it's natural to ask that is there some generalization to manifolds with boundaries, in particular torus boundaries. Okay, actually, I'm ahead of my time, but anyway, let me just stop here. Thank you.
Okay, thank you very much, Pavel. I'll just unmute the participants so they can give you a round of applause. Okay, and now to the questions. We've already got 2 questions. Maybe Edward Witten first. Let's see.
Okay, so thank you for the talk, Pavel. I had 2 kinds of questions. First, a very quick one, and then a sort of a category of questions. So the quick question is, you had those 3 manifolds that are gotten by surgery on a certain class of graphs. Are they actually Seifert manifolds? I know Seifert manifolds can be constructed that way, but I'm questioning whether all manifolds in the class you were considering there are Seifert manifolds.
Pavel, you just still muted. Just a second, Pavel. Sorry, Pavel, you're just going to have to unmute yourself and answer again.
Can you hear me now?
Yeah.
We can hear you now, yes.
Okay, so Seifert manifolds are the ones which can be realized by plumbing with star-shaped plumbings.
With what?
The plumbing of a star shape. When we only have, of this type, where there's one node of high valency and there's some rays going in some directions. These are Seifert manifolds.
Are you sure that more general ones are of the class you consider are not Seifert manifolds?
Well, if they, I mean, they can be. If one can find a sequence of moves to bring them in this form, they are also Seifert. But if there is no sequence of moves which brings them to this star shape, they're not. In general, they're not Seifert.
So Seifert manifolds have the property that the 3 manifold invariant can be expressed just in terms of the S matrix, the SL2Z mapping in genus 1, and not the R matrix. Is the same true? Is the same true for this whole class of manifolds?
Yes, yes.
I'm a little surprised. Well, that's obviously a drastic simplification to express them just in terms of the S matrix. And I'm a little surprised. It doesn't really quite contradict anything I know, but I'm a little surprised that there are 3 manifolds that aren't Seifert manifolds with that property. So, okay, I can't say more though. My general class of questions is the following. You described a number of constructions algebraically, but as a physicist, one would like to know if there's a path integral representation that corresponds to it. As one example, you had 3 manifolds colored by certain data, and associated with that, you would give invariance of the group SLN/M. What crosses my mind is that if you take the group SLN/M, pi1 of that group is Z. So in the language of Seiberg and others, it has such a gauge theory has a 1-form global symmetry, and you could couple to a background field. So an obvious question is whether your invariants colored by certain data are what you would have gotten by coupling the 1-form global symmetry to a background field. But whether that's the right interpretation or not, one would want to have a path integral interpretation of what you were doing. Well, you can comment on that, and then I'll give another example.
Well, yeah, I mean, we haven't worked out this. Yeah, this is a good, but I believe this indeed should be. I think there is such understanding, for example, for the case of U1 bar 1 case, and it should be something similar here. Yes. But
Okay,
I mean,
that would be illuminating. Otherwise, it sounds like something pulled out of thin air with no context. At least as a physicist, it's much more interesting if there's a natural context for the formulas. Another example, okay, so the volumes of the supergroups you're considering are 0, and that causes some invariants to be uninteresting if you follow the standard definitions. Then you mentioned alternative definitions with modified traces and such. Again, it would be, I think, more interesting if there's a path integral interpretation of what that is. I actually can only suggest what it is in a special case. Instead of 3 manifold invariants, you can consider not invariants in S3. For a compact Lie group, it doesn't matter very much if you work in S3 or R3. The two sets of invariants differ by a factor of a sort of renormalized volume of the group, which is just a non-zero constant. But for a supergroup, that factor can be 0. And so it makes a big difference if you're in R3 or S3. So not the most general case, but special cases of the not invariants that you would get with modified algebraic recipes simply correspond physically to working in R3 rather than S3. So for example, when you had 3 manifold invariants, an obvious thing you could try to do to get rid of a trivial problem with the volume of the group being 0 is to remove a point from your 3 manifold and project it to infinity so that you have a non-compact 3 manifold that's asymptotic to R3. I don't know if that would give the things you were talking about for 3 manifold invariants, but if it did, that would be, to my thinking, more illuminating than saying that there's some crazy algebraic formula that gives 3 manifold invariants. That could lead to
I mean, yeah, the path integral or the precise path integral interpretation still, kind of, we don't have it, but yeah, indeed, at least naively one can expect this omega is, for example, omega here is correspond to a certain background, turning on some background field.
But what I suggested was the only background field I could see. But sorry. Okay. Maybe I should stop there. There might be other questions.
Okay, thanks. In that case, we also have a question from Sergei Gubov. If you just want to unmute yourself and go ahead.
Hi, panel. Thank you. This was very nice. I have a quick question about the Q-series nature of the answers. Do they coincide or relate to characters of any vertex algebras based on supergroups? That would shed some light on the nature of this.
Yeah, it's a good question, but yeah, I don't know. Well, at least nothing what I would heard, but I'm very far from being an expert on some logarithmic VOA. But well, I mean, let me. Okay, so one thing I can say maybe it's like, for example, this. So the case of, for example, length spaces and S3. So this is kind of has a very kind of rough quantum modular property. So this may have a chance to relate to some sort of character of some bad enough VOA. But for example, already for this case, it's well, first of all, it's not. It's like, at least from these recursion properties, this for the Zabach manifold from the recursion properties, it seems that there is no no even remotely nice modular properties.
Okay, maybe we can come back to Edward, who has another question. Edward, you just need to unmute yourself.
I just wanted to clarify the question about your surgery on graphs. When you say that generically those are not Seifert manifolds, you're considering Seifert manifolds where the base has genus G, not necessarily genus.
No, I'm considering. I'm saying this Seifert with base being sphere.
Okay, but my question was whether general manifolds that you considered are Seifert manifolds with a base of genus G. I suspect they are. I'm totally non-expert on the three manifold theory, but I suspect they are for the following reason. General Seifert manifolds, which are just three manifolds with what's called a semi-free U1 action, a U1 action that's generically free. Those are the ones in which Chern-Simons theory can be studied by localization. And that leads to simple formulas, which manifestly only involve the S matrix. And the Chern-Simons invariants in those manifolds are then much, much simpler than the case of a generic three manifold. And the ones, again, I'm extremely forgetful, but as far as I remember, general surgeries on the class of graphs you drew also always lead to formulas involving the S matrix. And I'm just pretty sure that those classes of manifolds coincide. And I think it's important to know that for the physical interpretation, because you see, when the three manifold has a circle built into it, because it's a Seifert manifold, that gives a lot of possibilities for dual transformations to other pictures that aren't present generically. So whether the base had genus 0 wasn't important in my question. What the question was really getting at was whether you were discussing the same class of three manifolds where Chern-Simons theory can be treated by localization.
Well, there is a certain circle action, but I don't think, well, at least my knowledge tells me that there's not always generically, it's just Seifert manifolds with some other base. Because I mean,
hang on, Edward, you just muted again. Do you want to just unmute yourself? And
am I muted?
No, okay, yes. If you know there's an S1 action, that means they are Seifert manifolds. That's what a Seifert manifold is. It's a three manifold, well, except for very special cases. Generically, a three manifold with an S1 action is a Seifert manifold. But regardless, from my question, it's not important, even if there are exceptions. Three manifolds with S1 actions are the ones that can be studied by localization. So if you know your three manifolds have S1 actions, that means you're talking about the three manifolds that can be studied by localization. That's what I was trying to ask in my question.
Pavel, I don't know whether you want to, whether you're thinking or want to reply.
Well, I'm thinking if I can reply.
Okay.
No, I don't think it's actually, sorry, what I said about there is no global S1 action, because essentially one can understand these plumbing manifolds on general, so we have a kind of different basis. So what we can do, like as for Seifert manifold, we can if we just like start with some circle figuration, we can instead cut out some fiber and glue in fiber with SL2Z transformation. But we can also start with a pair basis of pair base circle figuration and glue the fibers together using some SL2Z transformation. But this SL2Z transformation which actually will change the circle on the base and the circle on the fiber. So actually, yeah, probably was wrong that there is a global, always global S1 action for general plumbing. Yeah, maybe I'm terribly mistaken, but I thought that these are not in general equivalent to just Seifert. Maybe someone can correct me. Only when the well, if you consider the case of tree plumbings, only when they are star-shaped. Like if it's not a tree plumbing, indeed, if there are some cycles, then it can be equivalently understood as a Seifert manifold with a high genus base.
Oh, I think Edward wanted to say something again. Yeah, please just unmute yourself, and we'll give this another minute or so, and then I'll just move on to another question that was hanging about. But Edward, please go ahead if you wanted to reply to this. No? Okay. I'll just lower the hand then. So there was another question from Mina Ganagic. You want to unmute yourself?
Okay. Thank you, Pavel, for a wonderful talk. I had a comment and a question. So what Edward said about the relation of S3 versus R3 is almost certainly correct, because if you were to consider knot invariance in U1/1 theory, you have to cut the knot, which I think means that you have to take one point of it away to infinity. Otherwise, the invariance simply vanishes. But my question was whether, you understand the need for rewriting the theory in terms of z hat, also in the U1/1 case. Does that arise as well? Of course, the U1/1 case is so much simpler, but has this been understood?
I think, yeah, so one can relate essentially z hats to, well, up to Fourier transform. In that case, z hats are essentially just torsion, more or less. Yeah. Or yeah. But in this case, the dependence on Q, the non-trivial dependence on Q, it goes away.
Okay. Maybe we've got a chance for one final quick question, if anyone has a final quick question. Otherwise, oh, hang on. Mina wants to reply. Okay, Mina, you should be able to unmute yourself. I think you, let me just find you and do it otherwise. There you go. Okay, Mina, I think.
Okay, good. And so then I have another question, which is perhaps a question to Edward, whether he sees the relation between the two viewpoints he suggested of interpretation of this extra data.
Okay, Edward, if you're going to reply, just unmute yourself. Just going to.
Okay, now.
There you go. Sorry.
So I think Mina's asking if I can see that gauging the one-form global symmetry gives what Pavel was describing. Well, I can't do that in real time, in part because I don't know what Pavel was describing. But, well, a preliminary step would be to just see whether it depends on the same data. I think what I was asking about would have involved a class in H1 with values in U1. But I'm not sure if that's right.
I mean, this, yeah, C mod Z essentially is U1. Okay.
What's that?
Well, I mean, more physically, C mod Z should be understood as U1.
Okay. Oh, you have a class in H. Oh, but you have two copies of C mod Z.
Yeah, I mean, roughly they correspond to two Cartan, two directions in Cartan, supposedly.
Okay, but see, I'd have trouble because pi1 of SL2/1 only has one Z, not two Zs, I think. Or am I wrong? Yeah, that's correct, yeah. The bosonic subgroup is just U2, roughly. But pi1 will only have one Z. So I'd only be able to see one kind of twist, not two of them. Do the two twists both have interesting information, really?
I'm just going to have to very quickly interject here. Sorry about this, but I believe Jeff is going to start setting up the next talk, and I'm not going to be chairing anymore, so I might be using Zoom roles, and unless Jeff can do things in parallel, there might be some confusion with muting and unmuting. So I'll just say thank you from my behalf, and I don't know if Jeff can, and some of the other co-hosts who are staying co-hosts can help with muting and unmuting. Okay, actually, Jeff
would we be able to turn on this extra one-form global data only if we puncture the S3? to make it into R3?
I don't immediately see how. But to me, the most interesting thing about this construction that Pavel was describing would be to understand physically what these twists mean. They're all, okay. At a minimum, it would make it much more interesting, but what I would find most interesting about it was simply to understand what you have to do to define these invariants in a natural physical way, which would mean somehow starting from the path integral, hopefully. And for your graph manifolds, I'm extremely surprised if there's a class of manifolds other than Seifert manifolds, where the partition function can be written just in terms of the S matrix. But if it is, I think it's important to understand physically what's the origin of the simplicity. We now know Seifert manifolds that the origin of the simplicity is localization, or the ability to calculate by localization. If there's really a more general class of three manifolds, where the three manifold invariants of quantum invariants are simple, in the sense that they can be computed just from the S matrix, we should be looking for what's the explanation that generalizes localization. Or is there a more general approach to localization that we don't know about that applies for this class of manifolds, or something?
Maybe I can just suggest, so there will be a breakaway session at 7 o'clock South African time, which I believe would be a perfect setting to discuss this further in a way which won't delay the next talk. So that is in 2 hours time, wherever you are. And hopefully that will be a good setting to discuss this further. Anyway, so thanks again to Pavel. I think Jeff will now start setting up the next talk. Sorry about this.
Thanks, Emmanuel. So actually, I just want to announce very quickly before we go to the next speaker that we're going to, following on what we did at strings, we're going to have a similar breakaway session, and we'll organize the breakaway sessions by the 2 sessions of today, just because the number of participants that we have is slightly less than strings. So as per usual, I will make an announcement close to the end of the day, just requesting which session people would like to be put into. Unfortunately, they will have to be put into manually, but we'll try and get that done as soon as possible. And then at the end of the day today, we will put people into the breakaway session. So thank you again, Emmanuel, for chairing that session. Our next session chair is Ines Aniceto, and she will be introducing the next speaker in the next session.
Thank you. So I think we have 1 minute. No, it's basically about time. So I'm very happy to introduce Eric Sharp from Virginia Tech, who will be talking about gauging one-form symmetries in 2D theories. So, okay, I can see your screen.
Can you hear me?
Yes, as well.
Wonderful. All right. Well, thank you very much to the organizers for inviting me. It's a pleasure and an honor to speak here today. I'm going to be talking about gauging one-form symmetries in two-dimensional theories, which, as you can tell from the reference list I provided, is perhaps something I've wasted too much time on over the years. And in particular, I'll be talking about a new wrinkle or perhaps a bookend to my thoughts on this over the past while. So the main theme of this talk is as follows. Well, obviously, I'll be talking about two-dimensional theories with finite global one-form symmetries, and I'll review how they seem to be equivalent to a disjoint union of theories with no one-form symmetry, which are sometimes been called by various people universes. This is what I'm going to mean by decomposition in this talk. Now, that part of the story is relatively old, but it's also somewhat obscure. So I'm going to spend much of the talk sort of reviewing why in the world such a statement appears to be true. Then the new thing, the reason for the talk, is that I'll be talking about gauging that one-form symmetry. And gauging the one-form symmetry simply acts as a projection onto components. And amongst other things, I'll walk through the details of mechanically how in the world that actually turns out to happen. Now, there's a secondary theme to this talk, which is somewhat entertaining. Two-dimensional theories with global one-form symmetries have several different descriptions. One description, which is probably the main one I'll be talking about today, is as a gauge theory with a trivially acting subgroup, trivially acting on all the massless matter of the theory. Another description that sometimes appeared is as a theory with a restriction on instanton sectors, which immediately suggests that these theories could suffer from issues with cluster decomposition. I'll come back to that later. A third description of these theories is as sigma models on gerbs. So a gerb is basically a fiber bundle in which the fibers are copies of the one-form symmetry group, which is sometimes denoted G1, but in this talk I'll be denoting by a BG. So if I have a sigma model on the total space of a principal G bundle, that sigma model will have a global G symmetry from translations along the fibers. And the same thing is true here. If you have a sigma model on a gerb, then there'll be a global symmetry due to translations along the fibers. The only difference here is that the global symmetry is a one-form symmetry rather than an ordinary zero-form symmetry. And then finally, another description that's often popped up in the literature is in terms of coupling a quantum field theory to a topological quantum field theory, which is fine, but it's not something I'm going to have the time to talk about today. So as a secondary theme, one of the things I'll do is discuss explicitly how this decomposition I mentioned into what have sometimes been called universes implements that second description as a restriction on instanton sectors. Essentially, the restriction on instanton sectors pops up as what I laughingly sometimes refer to as a multiverse interference effect, as the contributions from the different universes interfere with one another, which relates some of these pictures. All right, so here's an outline of what I'm planning to do in the next 35 minutes. I want to begin with a brief overview of one-form symmetries and two-dimensional theories. Now, at this point, one-form symmetries are probably, just taken in many quarters to be a staple of quantum field theory, but I've still run into lots of people that maybe aren't always up to speed. So I think a one slide briefly overviewing that seems wise. Then I'll walk through a brief overview of decomposition of two-dimensional theories with finite global one-form symmetries. And then in the remainder of the talk, I'm going to focus on one, or if there's time, two simple concrete examples. The first example will be an orbifold with a Z mod 2 one-form symmetry. I'll walk through explicitly how decomposition works in that case, and then I'll talk about how one can explicitly gauge that one-form symmetry. And then if there's time, I'll perform the analogous analysis in a pure non-supersymmetric SU2 Yang-Mills theory. I'll explicitly describe how decomposition arises, how to see it, and then I'll explicitly gauge the one-form symmetry in that context. Now, to be clear, this only scratches the surface. There are more examples, there are more kinds of examples, there are fun applications, but this is a relatively short talk, so I just wanted to focus on a few basic things. Now, what's a one-form symmetry? So again, this is often described in terms of actions on defects, but for this talk, I want to focus just on local quantum field theories themselves. For this talk, intuitively, a one-form symmetry will be a group, or something like a group, that exchanges non-perturbative sectors in, well, in this case, a two-dimensional theory. So for example, if I have a G gauge theory in which the massless matter is invariant, or in which the matter is invariant under some subgroup of G, let's assume it's finite and abelian, then the non-perturbative sectors, the non-perturbative contributions to the path integral are invariant under this permutation of the possible sectors. I can take a G bundle and essentially replace it with that G bundle tensored with a K bundle. And because all the matter is invariant under K, that will give rise to a symmetry of the quantum field theory, just an interchange of the non-perturbative sectors. So this is the one form symmetry involving something that's basically a group of K bundles. And that group I'm going to denote by BK. Now I've put group in quotes there because one should be slightly careful. In an ordinary group, for example, if I take a group element and multiply it by its inverse, I get the identity. In this context, if I take a group, well, a group element, a bundle, and multiply it by its inverse, I get something that's isomorphic to the identity. So instead of having honest equivalences, one only has isomorphisms. And so it's not really a group, it's sort of the next best thing to a group. But that detail isn't really going to play an important role in this talk, but it's worth pointing out. Now, suppose you have a 2D QFT with a finite global one-form symmetry. There's an old result that such theories decompose into disjoint unions of theories without a one-form symmetry. Now, let's make that concrete. So decomposition, let's do this in two-dimensional gauge theories. Suppose I have a G gauge theory. Let's suppose G is semi-simple with a finite subgroup acting trivially. And for simplicity, let's assume K is in the center and that the resulting one-form center symmetry is not obstructed by some other mechanism, so that the theory has a BK symmetry. So in this case, the claim is that the quantum field theory of that two-dimensional gauge theory should decompose as a disjoint union of quantum field theories of G mod K gauge theories with various different discrete theta angles. So for example, a pure SU2 theory would then decompose as a sum of two copies of an SO3 theory, one with either value of the discrete theta angle. The discrete theta angle just being an analog of a theta angle that couples to a discrete degree 2 characteristic class. In this case, a G mod K gauge theory would have a K valued degree 2 characteristic class. And so we have a set of discrete analogs of theta angles corresponding to characters of K. There's another version of this for analogs of nonlinear sigma models. There isn't time to walk through that today. Now, one effect of this decomposition is to implement a projection on non-perturbative sectors. And so I've tried to illustrate very formally at the bottom how that works. On the left, I have a disjoint sum of path integrals involving just a sum over the possible discrete theta angles. And on the right, I've taken that sum and moved it inside the path integral measure. And when I do so, that sum over discrete theta angles and that weighting of the path integral measure combine to form something that is proportional to a projection operator. And schematically, this is what I mean by decomposition implementing a projection onto non-perturbative sectors. That sum over components, that sum over universes is, at least in this formal argument, implementing a projection operator. Now, since 2006, we've checked decomposition in a bunch of different examples in a bunch of different ways. In gauge linear sigma models, we can compute mirrors and quantum cohomology rings, and the structure falls right out. In orbifolds, we can compute partition functions in massless spectra and elliptic genera, and the structure basically falls right out, as I'll review in an example in a few minutes. You can see this in open string theory in the context of a gauge theory. Just because the gauge group acts trivially on the bulk fields doesn't mean it necessarily acts trivially on the boundary fields. So you get essentially copies of the possible boundary fields indexed by irreducible representations of that trivially acting finite group, as a consequence of which you have a decomposition of the open string sector. You can see this in open string theories via localization. Partition functions, two-sphere partition functions naturally decompose in this fashion. One can play this game in non-supersymmetric pure Yang-Mills theories. I'll briefly outline towards the end, if I have the time, how that works. Nowadays, there's even a version that was worked out recently for four-dimensional theories with three-form symmetries. Let me take just a minute to emphasize that what I'll be talking about is a two-dimensional theory with a one-form symmetry. And I'm not going to talk about other dimensions. If one wanted to talk about other dimensions, well, the type of form symmetry would change. Now, the reason we've done all this is that there are some fun applications of this, or at least fun for me personally. This makes some predictions for Gromov-Witten theory, which were checked in a series of papers starting in 2008. One can use approximate one-form symmetries to understand phases of certain gauge linear sigma models. This is probably my favorite application of these particular things. There won't be any time to discuss it today, but if anyone's curious, ask me later. And this is also pertinent to recent discussions of moduli spaces appearing in string theory. Here, there's not a decomposition story per se, but the same mathematics appears in understanding moduli spaces. Basically, many of these moduli spaces necessarily have some sort of finite gerbe structure, which is reflective of various t-dualities and plays an important role in various things. But that's beyond the scope of what I can do in this talk. Let me mention one other quick example before going on, involving vacua of pure supersymmetric gauge theories. So for a pure G mod K gauge theory in 2 dimensions, for a pure supersymmetric G mod K gauge theory in 2 dimensions, it turns out you get supersymmetric vacua for one choice of discrete theta angle, and supersymmetry is broken for other choices. I've outlined the results here. For SUK mod ZK, for example, there's a Z mod K's worth of choices of discrete theta angle. It's the one given in that first entry, the -1/2 K, K minus 1 mod K, that for which you actually get non-trivial vacua. For that one particular discrete theta angle, the infrared theory is believed to be the same as the original, or as the SUK gauge theory itself. And there are no vacua in the, no supersymmetric vacua in the other, for other choices of discrete theta angle. So this is consistent with decomposition. Decomposition in this case just says that basically the G gauge theory should be equivalent to a disjoint union over G mod K gauge theories. And basically what I'm saying is that the sum of the supersymmetric vacua on the right-hand side matches the supersymmetric vacua on the left. I should also add decomposition is just a structural result in this case. Decomposition does not uniquely predict which theta angle. It doesn't even distinguish other choices. For example, it might have been that the vacua appearing at that one discrete theta angle were actually spread over multiple different discrete theta angles. Nothing about decomposition said they all have to lie in just one, but this is just a structural result. It's yeah. So suffice to say, decomposition seems to be well established, or at least after fiddling with this for years and years and years, I have yet to find a counterexample. If anyone can think of one, by all means, get in touch. I'll be happy to take a look. Now, what I want to do next is walk through a simple example. First, to try to demonstrate why this perhaps obscure looking result actually works, and then to describe how exactly one gauges that one form symmetry in that context, which is the new piece of this particular story. It's in principle the reason I'm giving a talk today. So let's consider an orbifold of a space, some Clabial, by the 8-element group D4. Now, D4 has a Z mod 2 center. Let's assume that center acts trivially on the space X. So from what I've outlined before, the theory has a BZ2 symmetry. Now, if I quotient D4 by the center, I get the group Z2 cross Z2. So this theory is going to be closely related to a Z2 cross Z2 orbifold. Now, in this context, in this example, decomposition predicts that that D4 orbifold of X should be the same as a sum of Z2 cross Z2 orbifolds, one with discrete torsion, one without discrete torsion. This is a consequence of a general formula, a general prediction for decomposition, which has been written down for analogs of nonlinear sigma models. I'm not going to have the time to walk through the details. If you're curious, ask me later. But suffice to say, it's a consequence of a formula, not just some random observation. Now, let's check that. Let's check it by, for example, computing the partition function. Now, to do that, if you'll bear with me for a second, it'll be helpful to actually walk through the possible group elements. So D4 has 8 elements. I'm going to label them 1Z, A, B, and various products thereof. The Z generates the Z mod 2 center. And A and B do not quite commute with one another, as is visible in that table there. if I take the quotient by Z2, what I get is a Z2 cross Z2 orbifold, whose elements I'll label by 1 A bar, B bar, and AB bar, where the overline is just to indicate that one's working with that coset. Now, the partition function of this theory is, let's see, easy to write down formally. For any orbifold, we take the one loop partition function as 1 over the order of the orbifold group times a sum over commuting elements times path integral contributions that look like maps from basically a torus with branch cuts, if you will, into the target space. And I've indicated those contributions by this here. Now, since Z acts trivially, these contributions are symmetric under multiplication by Z. That generates the trivially acting center. So this contribution is the same as that one, as that one, as that one. And the first observation I want to make is that these different sectors are all related by Z2 bundles. One way of thinking about these commuting pairs is that they are defining principal D4 bundles over the 2 torus. I can get from this D4 bundle to this D4 bundle by tensoring with this Z2 bundle I've indicated down here. So these different symmetrically contributing sectors are related by multiplication by Z2 bundles. And this, in this context, is the BZ2 one-form symmetry. Now, so far I've told you that each D4 twisted sector that appears is the same as a Z2 cross Z2 twisted sector, appearing with multiplicity 4. There are basically 4 different classes of Z2 bundles I can multiply in, except for these 3 sectors which don't appear. The reason they don't appear is that they do not correspond to commuting pairs of group elements inside D4. If I tried to lift A bar and B bar to a pair of elements in D4, well, the natural guess would be A and B, but A does not commute with B. BA is ABZ, it's not AB again. So that cannot appear inside the D4 orbifold. Similarly, these 2 sectors cannot appear either. So this is the restriction on non-perturbative sectors that people sometimes talk about in connection with one-form symmetries. Here we are, this partition function excludes some of the non-perturbative sectors that would have appeared in a Z2 cross Z2 orbifold. Now, computing the partition function, we have that the partition function of the D4 orbifold looks a lot like the partition function of that Z2 cross Z2 orbifold, except we've subtracted out some sectors. And if we're going to be careful, we also need to worry a little bit about multiplicative factors. They turn out to just generate a factor of 2. Now, the next point I want to make, which I think will probably be obvious nowadays, but bear with me, is that this is different than a Z2 cross Z2 orbifold. I emphasize this for historic reasons. When I first started talking about these theories a long time ago, one of the main complaints I got was that surely if the Z2 acts trivially, you're going to get the same result as a Z2 cross Z2 orbifold. There can't possibly be any meaningful difference. So after having fought that battle far too many times over the years, I just wanted to remind everyone that this theory really is different than just a Z2 cross Z2 orbifold. And in modern language, it's because of the existence of that one-form symmetry. Now we can say a bit more. Discrete torsion in the Z2 cross Z2 orbifold is just a Z2, and it acts as a sign on precisely these same sectors, which were omitted above. So a more useful way to write this particular partition function is as a sum of 2 partition functions, a sum of 2 Z2 cross Z2 orbifold partition functions, one with discrete torsion, the other without. Since discrete torsion multiplies the ones to be excluded by a sign, the effect of adding these things together is to cancel out these contributions. And the result matches the prediction of decomposition I mentioned earlier, that the conformal field theory of that D4 orbifold should match the sum of the conformal field theories of the 2 Z2 cross Z2 orbifolds. Now, let me tell you a few more things about this before going on. At the level of operators, one reason for this is the theory admits projection operators. If I hat denotes the dimension 0 twist field associated with that trivially acting Z2, then I can build a projection operator onto either of the 2 components, or I can build projection operators that look like this. And that's one way in terms of local operators to see why there are 2 components. In terms of massless spectrum, well, we can compute the massless spectrum of the D4 orbifold. It's straightforward, but the first time I saw it years ago was a little bit confusing. Here I've, saying I'm computing the massless spectrum, I've taken X to be T6. I've let the Z2 cross Z2 act as pairs of sign flips on 2 tori inside that 6 torus. So this is closely related to a old standard example of a toroidal orbifold, a 6 torus modulo as Z2 cross Z2. If I do this for the D4 orbifold, I get this. It's got more stuff than the massless spectrum of a Z2 cross Z2 orbifold, basically because some of the non-perturbative sectors were omitted, so the projection operator in the orbifold is weaker than it would have been. I've arranged the result into a Hodge diamond. I work on string compactification, so it's a natural thing for me to do. And these 2's in the corners are a good signal that whatever this thing is, it's trying to behave like a disconnected space. It's trying to behave like 2 copies of a space, not just 1 space. And indeed, if you compare the spectra of Z2 cross Z2 orbifolds with or without discrete torsion, they take these forms here. And it's easy to see that adding these together gives the D4 orbifold spectrum. So again, that's consistent with the prediction of decomposition, that the D4 orbifold should be the same as a pair of Z2 cross Z2 orbifolds. Now, all of that was new. Let me try to get to something that's, or all of that was old. Let me get to something that's actually new. Let me describe how to gauge that BZ2 in this context. So in broad brushstrokes, what should gauging that BZ2 one-form symmetry look like? Well, the partition function should look like 1 over the order of, if I'm going to gauge a BG, I would expect that the partition function should look like 1 over the order of G times some sum over G gerbs of sectors twisted by the G gerb in the sum. So I've got some path integral over BG non-perturbative configurations, if you will, and then in each of those I have something twisted. So in this case, I have a BZ2 I want to gauge. So I have a 1 over the order of that Z2 times a sum over gerbs, banded gerbs, it turns out. There's a more general class of gerbs which don't arise in the sum. If anyone's curious, ask me later. Here is the sector twisted by the gerb. This looks like the partition function of a D4 orbifold, except that the bundles appearing are all bundles that are over a gerb on T2 rather than over the T2 itself, which means as a practical matter, the G and H only have to commute up to multiplication by Z. And then finally, there's a phase we can add to weight these contributions differently. It's some analog of discrete torsion that arises in this context. Now, again, these GHZs are gerb twisted, orbifold twisted sectors. That's a mouthful. If anyone has a better name for it, let me know. For Z in the center of the orbifold group, SL2Z will map a sector like this to a sector of the same form, preserving Z. For more general Z's, modular transformations will map Z to a conjugate. That's beyond the scope of what I can talk about in this talk. Finally, these phases, epsilon, are constrained to form a group homomorphism from Z2 into U1. That's partially as a result of multi-loop factorization. Now, let's put this together. So suppose we take Z to be 1. Then in the contribution from Z to where Z is 1, this is just the ordinary partition function of the D4 orbifold, which, as mentioned before, looks like twice the partition function of a Z2 cross Z2 orbifold minus some sectors. In the sector where Z is different from 1, this is just a Z2, so there's only one such sector. Well, the only contributions are going to be from group elements that commute up to the action of Z. And the only possibilities are these 3 here, which turns out to be exactly in one-to-one correspondence with the sectors excluded from the Z2 cross Z2 orbifold. So now you can probably sort of guess how this is going to work. If I want to construct the partition function of the D4 orbifold in which I've gauged the BZ2, I'm going to add these 2 possible contributions weighted by the epsilons. Now, since epsilon is a group homomorphism, epsilon1 is equal to +1. The interesting value is epsilon at -1, epsilon on the non-trivial element of Z2. In one case, the effect of adding these together is to cancel out these two terms. So if this phase is equal to +1, then I recover precisely the partition function of the ordinary Z2 cross Z2 orbifold. If this phase is -1, then the effect is to essentially subtract this twice. So these sectors appear, but now weighted by a minus sign, which means that's the partition function of the Z2 cross Z2 orbifold with discrete torsion. All right. Now recall decomposition in this case. Decomposition said that the D4 orbifold should be the same as two copies of a Z2 cross Z2 orbifold, one with discrete torsion, one without. We got both of those possible objects as consequences of gauging the BZ2. There was a choice in this particular phase, this analog of discrete torsion. The upshot is that gauging that one form symmetry has projected onto the components. So that's a fun game in orbifolds. I think I've got enough time to quickly walk through one more different kind of example in which this happens. Let's consider a pure non-supersymmetric SU2 Yang-Mills theory. So in a pure non-supersymmetric SU2 Yang-Mills theory, there is on the face of it a global BZ2 center symmetry. Decomposition predicts that SU2 theory should be a sum of a pair of SO3 theories, one with either value of the discrete theta angle. So in terms of partition functions, this is straightforward to check. From Migdal and Rusikov's old work in the late 80s, the partition function of the SU2 gauge theory is a sum of this form in which we sum over all SU2 representations. For the SO3 plus theory, the SO3 theory with no discrete theta angle, you have what looks like an identical sum, except that it only involves SO3 representations rather than SU2 representations. Now to see this, we need the partition function for the SO3 minus theory. That was essentially worked out by Yuji Tachikawa back around 7 years ago, and Yuji's conclusion was that the partition function of the SO3 minus theory should look, well, basically have the same form, except you should sum over all the SU2 representations that are not SO3 representations. So the effect of turning on the discrete theta angle is to sum over representations of the covering space group with the right anality. So the result then is the partition function obviously decomposes. A sum over SU2 reps is the same as a sum over SO3 reps plus a sum over the remaining SU2 reps. And in fact, this is easy to generalize. So let's see. More generally, if I have some pure non-supersymmetric two-dimensional G Yang-Mills theory, and G has center K, then one expects a decomposition of this form, of the G gauge theory into a sum of G mod K gauge theories, where the thetas are discrete theta angles coupling to analogs of Stiefel-Whitney classes. There's a similar decomposition that's easy to write down for the Hilbert spaces. The Hilbert space of a pure G Yang-Mills theory is the L2 class functions on G, and these have some natural decomposition under the action of the center. The Hilbert space, one can argue for the G mod K gauge theory with discrete theta angle theta, consists of those particular L2 class functions on G that transform like this under the center. And so for essentially trivial reasons, it's easy to see that the Hilbert space of the G gauge theory is a sum of the Hilbert spaces of the G mod K gauge theory. Now, let's see how to project, let's see how to gauge BK. What does it mean to gauge that BK center symmetry in this particular context? So broadly speaking, much as before, the partition function of a BK gauged gauge theory should have this form: 1 over the order of K, a sum over K gerbs on the world sheet, some phases, some analogs of discrete torsion, and then the gerb twisted contributions. So these z's are the partition functions. ZZ is the partition function in a sector twisted by a k-gerb of characteristic class Z. Now, to define the gerb-twisted gauge theory partition function, if you've seen the old McDowell-Rusakov way procedure, basically is going to involve coming up with some sort of twisted cap. So the game they play is to come up with functions to associate to various pieces of Riemann surfaces with group elements associated to components of the boundary. So for an ordinary cap, the corresponding function, the contribution from that cap looks like this, a sum over pertinent representations of this function. This is a character of the group element corresponding to the Wilson line along the boundary, and the representation R, the one summing over. The partition function for a two-sphere can be obtained by taking two of those caps, sticking them together, and then integrating out the Wilson line along the joint boundary. The result looks like a sum over representation. Well, the result is the special case of what I wrote down before for genus 0. A twisted cap is very similar. The difference is instead of having just the character of U, we have the character of U times Z. And the effect of that is to pull out some other phase factor. So putting this together, the partition function of that pure G gauge theory in which the BK has been gauged is again a partition function of this general form. Plugging in Z of Z, plugging in epsilon, one gets an expression like this. This sum over gerbs becomes a projection onto representations of fixed anality determined by the essentially the choice of phase epsilon. And then with that particular representation, the result is a sum over what looks like the same partition function as before, except now with a restriction to representations of the covering group of a particular fixed anality. In other words, it's the partition function of the G mod K gauge theory with discrete theta angle lambda. So the effect of gauging that BK with a phase determined by lambda is to select one component of the decomposition of that two-dimensional pure non-supersymmetric theory. All right, so far I've reviewed decomposition, which I emphasize is in my talk has just been a property of two-dimensional quantum field theories with a finite global one-form symmetry. And I reviewed how to go about gauging that one-form symmetry. So what about quantum field theories in other dimensions? So for four-dimensional theories, Yuya Tanizaki and Mehret Unzel worked out an analog of this past December in four-dimensional theories with a finite global three-form symmetry. There's a natural conjecture here they speak about a bit that there should be some analog of this for quantum field theories in d dimensions with a finite global d-1 form symmetry. I don't think any of us have really worked through a lot of the details of that, but it's sort of the natural extrapolation of examples in these two sets of dimensions. And along that spirit, one can say a little bit more. If that's true, it's going to involve a d-1 form, and part of what's going on is that d-1 form will couple to a domain wall. So one ends up with something that's somewhat analogous to the old Busso-Polchinski picture years ago for nucleating membranes in four-dimensional theories to reduce the cosmological constant. It's analogous in the sense that one would have, in the four-dimensional case, a three-form coupling to a domain wall. There's no cosmological constant. There's no four-form with a non-trivial kinetic term that dynamically drives membrane nucleation, but at some level it's analogous. This is also consistent with reduction on a circle. That d-1 dimensional theory would have a, if I reduce on a circle, I get a d-1 dimensional theory with a d-2 form symmetry, which if the conjecture is correct would decompose. And furthermore, if the d-dimensional theory decomposes, then surely its reduction on a circle has to decompose as well. So is there any math here? This is a conference, this is a string math conference, and I think I've managed in most of this talk to speak only about the physics side of all of this. Let me, here at the end of this talk, briefly talk about corresponding mathematics, or at least place this in the world of mathematics. So far I've just talked abstractly about two-dimensional theories and one-form symmetries. So this can be interpreted mathematically in terms of gerbs. As I mentioned very briefly earlier, a G-gerb is basically a fiber bundle where the fibers are copies of that group of one-form symmetries. Furthermore, a sigma model on a G-gerb should have a global BG symmetry, just as a sigma model on the total space of an ordinary G bundle would have a global zero-form G symmetry from translations along the fibers. Furthermore, one representation of BG is as the quotient of a point by G. So, I mean, a good intuition is whenever you have a gauge theory in which a group is acting trivially, then the gauge theory is trying to implement this over every point of the Higgs branch. And so it's sort of natural to expect that there ought to be some sort of gerb structure or one-form symmetry lurking somewhere in the theory, unless it's been obstructed for some reason. Now, 20 years ago, I got into this because I was interested in studying sigma models on gerbs as possible sources of new string compactifications. There were a lot of headaches at first. There was, well, initially some question about how in the world you actually build a field theory that would correspond to this. There are questions about how cluster decomposition works, as I've touched on earlier in this talk. There were confusions about moduli. The moduli of the gerb, the moduli of the stack are not the same as the moduli of what one would expect as the corresponding physical theory. So there's a headache about why the moduli don't match. There are potential questions about modular invariance and unitarity and orbifold examples. There are issues with potential presentation dependence. Suffice to say, what we eventually learned was these theories are well defined, but because they're disjoint unions of ordinary theories, at least in 2-2 supersymmetric cases, but they're disjoint unions of ordinary theories, at least in 2-2 supersymmetric cases, because of decomposition. So we don't really get new string compactifications, but instead we do have some other fun offshoots I mentioned at the beginning. There are some predictions for Gromov-Witten theory, which were checked years ago. There are some fun games one can play with GLSM phases, which is certainly my favorite application of all of this. So finally, let me conclude with just a very quick schematic of why gauging BG in a theory with a one-form symmetry ought to result in an ordinary theory. Very schematically, a G-gerb is just a fiber bundle in which the fibers are BG. So locally, it's X cross BG. Gauging BG amounts to quotienting out the BG, which morally ought to leave you with something like X. Now, that doesn't account for non-trivial gerbs, these analogs of discrete torsion, or any of that. But if you forget everything else from this talk, this is a sort of quick and dirty way of understanding where it's coming from. So to summarize, I gave everyone a brief overview of one-form symmetries and two-dimensional theories. I've reviewed decomposition of two-dimensional theories with one-form symmetries, and I worked through a couple of simple concrete examples, in both cases giving an explicit description of decomposition and explicitly gauging that one-form symmetry, which is essentially the new wrinkle, and at this point more of a bookend to this particular line of thought. Last but not least, let me mention we're running an online workshop on gauge linear sigma models in the middle of August. If anyone is interested, you are welcome to participate. Let me again thank the organizers for inviting me and thank the audience for listening to me. That's it.
Thank you. I actually don't know how to unmute all, it seems.
I've done it.
Okay, so if everyone wants to thank you. And so let me mute everyone again. And so, sorry, can you unmute yourself again, Eric? So there's a few questions. Yes, sorry, it's just that I mute everyone and I wanted to unmute you. So we have one question already for a while, sorry, from Xing Tung Yao. Please, can you unmute yourself? Oops. So can you unmute yourself? Do you still have a question?
No, I actually did not ask any question.
Okay.
Sorry. I'm not planning to ask any.
So now then Gregory Moore, sorry. Can you unmute yourself, please? Oh, sorry, I can unmute you. Yes? Sorry. I seem to be.
Okay.
Okay,
there.
so now I can, sorry.
I was unable to unmute myself before.
I was unable to unmute you for some reason as well. So some
okay. Well,
glitch.
Okay.
Yes.
So Eric.
Sure.
Hi. I like to think of quantum field theory, at least conceptually, in terms of a functor from Bordism category to some other category.
All right.
It's a nice picture. But this idea of decomposition, disjoint union, or sums, or universes, quantum field theories doesn't seem to play that well with that notion. So if you have this kind of a Tia Siegel et al. Picture of what a quantum field theory is as a functor from a geometric Bordism category, perhaps with other structures, to some other category. Then in general, the direct sum is not going to make sense. And probably that's even true in the examples that you showed. So I just want to ask if that worries you. I mean, to me, it would seem that I'd like to preserve that kind of picture and perhaps expand the notion of fields. Well, I'm interested in how you.
I'm open to suggestions, Greg. I mean, this was, when I first started playing with these things, this wasn't an interpretation I came to lightly, I guess you might say. But the reason the thing I like about it is it gives a simple explanation for all the concrete computations I can do. So here in these simple examples, I've illustrated partition functions. I've spoken a little bit about Hilbert spaces. This applies to other cases. If you can compute the elliptic genera follow the same pattern. The quantum cohomology rings follow the same pattern. This even shows up in the mirrors. Now, I'm willing to believe that there's some other interpretation for it. If you can find an extension of the idea of fields that makes this work, I'm sort of game. I think way back when we first computed the mirrors, one of the weird things that pops up in the mirror, if you try to follow the Horry-Boffa prescription, is that you get, what at first looks like some sort of Z mod K valued field. And perhaps that's the extension of fields that you have in mind. But the thing about something that looks like a Z mod K valued field, in other words, a path integral trying to sum over roots of unity, is that seems to be functionally equivalent to having a sum of partition functions. I'm open to other suggestions, but I think my philosophy at this point is if you can find some other description that has all of the properties I've described, if you can find something else such that the massless spectrum of the theory decomposes as if it were a sum, something else such that the partition functions decompose in a sum, the elliptic genera decompose in a sum, the state spaces seem to decompose in a sum, something else with projection operators, something else with the quantum cohomology rings playing this game, something else with the mirrors doing this, something else in which the open string sectors naturally fall apart. If you can find another way of describing it, I'm all ears. But
well, we certainly, I mean, it's not unusual to find sums over topological sectors. And I mean, when I say extension of field, what I have in mind is a point of view that I've learned from Dan Fried,
Okay.
Is that you should really think of local, something like an orientation or a spin structure is really a local thing.
Okay.
You consider it as a field, a general notion of a field. And in particular, another thing I've learned from Dan is that if you have two-group symmetry, which is what you're talking about here, then what it really means is that you have a non-trivial fibration of your space of fields. So
walk me through this real quick. When you say a non-trivial fibration of the space of fields, you mean it's over those different components?
Well, this is going to, okay.
Yeah, but
and that comment would take us too far afield. But I just want to
okay.
Expect that one could, it doesn't really make sense to take a sum of field theories in the sense of Atiyah and Siegel et al. But B, that in your examples, perhaps by expanding the conceptual notion of what a field is, one could fit your decomposition of theories into the Atiyah Siegel et al. Framework.
Yeah, again, I'm game. What this might be. Let me get my glasses on and see what the time is.
Yeah,
this might be something that would be best discussed later, just for sheer.
In the breakaway sections.
Yeah. For example, I'm happy to play this game. I am happy for other interpretations. It's just that in the actual concrete computations I do, everything's consistent with this picture. There's one other point, which is, there's one other point. If I'm not certain I understand the fibration over the fields that you were referring to earlier, but if it's what I think you're referring to, then I think you might be thinking about the components in the wrong way. The different components aren't.
We can talk about it later.
Let's talk about it later. I don't think there's time now.
Yeah. So
but
now
I'm game. I'm happy to believe there are other interpretations. It's just that for years I keep doing computations. We get results that are consistent with this. And if I don't go that route, then the results become very confusing very quickly. The mirrors don't make sense anymore. They seem to explicitly fall apart. The quantum cohomology rings. I mean, I'm happy to play other games, but if this is not true, then I've got a whole pile of results that I don't know how to interpret usefully. I'll put it like that.
But maybe we still have a few more questions. So the next question, thank you. So the next question is from Nathan Seiberg. Oh, sorry. I just, unmute.
Okay, can you hear me?
I can hear you.
Yes.
I have a more lowbrow version of the same question. So we're in 1+1 dimension, so space is a circle. And the question is there an operator in your theory that acts on all of space that maps you from one of your sectors to the other?
No.
No?
And I can say that because I can build projection operators. Sorry?
In some of the examples you presented, there is such an operator. The operators that are charged under a one-form symmetry are lines. And if there is a line operator, so there must be charged line operators, and a line operator acting on all of space is going to map us to another sector. I can go through any one of your examples and do that. So it seems to me that the theory with the one-form global symmetry indeed has sectors, but these are not decoupled theories because the spectrum of operators in the theory includes well-defined good operators. They're not at the point operators, but line operators that map us from one sector to another. And that interpretation, I think, is much more conventional.
Yeah, let me think about this for a second. I think you may well have a point. This is, so I prefer to think about just ordinary local operators. And on the ordinary local operators, there are projection operators I can build. For example, in that Z2 and the D4 orbifold example. Yes, if you include Wilson lines, I mean, the thing that's puzzling, the place this might go wrong in the D4 example So as a simple toy model of, I could imagine a map from, I could imagine a string twisted sector with a, trivially acting Z mod 2, essentially a Z mod 2 twist field in the middle. So that sounds, if I could build a Wilson line out of that, bear with me for a second.
Maybe I should give you a
simpler example.
I think all this D4 is non-abelian and is unnecessarily complicated. The simplest example is just to look at the case where you have an ordinary Z2 global symmetry, spontaneously broken, so we have two vacua. But the flow energies, there are only two ground states. This happens, for instance, in the Ising model in the broken phase. I would say that there's in finite volume, there are two states, and there are operators that map us from one to the other. At infinite volume, the ordinary Z2 is spontaneously broken. And I think this is all you have. These are not decoupled theories. At low energies, they become decoupled. But if you include the line operators that connect them, then they are not decoupled.
So basically what you're
describing your super selection sectors.
So if I'm following you correctly, and I might not be, but if I'm following you correctly, you're talking about super selection sectors. Is that right? Do you agree?
Everything is in finite volume, so we don't even the notion of
good. That's okay. Good. That's because that was going to be my complaint.
Right. So we are in finite volume, and we have a standard quantum mechanical system with a standard looking Hilbert space. Nothing funny here. You don't need to break the rules of standard quantum mechanics and field theory to accommodate this.
Yeah, except this is. Let's talk about it more later. You may well have a point. There are a couple of things that, let me mention three things because I think I'm just about out of time. One is that you're not talking about super selection sectors, but if you were, then I would refer you to Yuya and Midhat's paper from last December, which explicitly looked at super selection sectors in these theories and argued that what's going on is a stronger version, stronger than ordinary super selection, that there are no they couldn't see any, they had an argument that there were no field configurations that the path integral would sum over which related the different universes. The second point was that if you had a just a string twisted sector, a string in that trivially acting Z2 twisted sector that actually, when you apply the projection operators, looks like a pair that decomposes into a union of two strings just mapping each of the universes to itself. It doesn't actually connect them. There's a confusion about what the universes are. They're not the same as twisted sectors. There's some linear combinations, which makes that story work. And there was a third point I'm blanking on, but I think I'm just about out of time. So yeah, you may have a point. Let's chat about this some more later. I'm happy to believe, as I told Greg, I'm happy to believe that there is some alternative or more subtle interpretation of what's going on. It's just that in all of the computations that I've been doing for years and years and years, everything is consistent with this particular interpretation. I'm happy to believe you may well be onto something, but then we need to have a much longer discussion about, oh Lord, about how all these other computations are then consistent in that context and what exactly they mean.
So perhaps this is a good conversation to have in the breakaway. I think that there's 1 more minute for one last question. Sorry. So it's Hank Chen.
Hi.
Hi.
Hello. Can you hear me?
Yes.
Yes, I can.
Okay. Thank you for the talk, Eric. It was very enjoyable. So I guess my question is like what this decomposition looks very much alike is there's something called dimensional reduction in condensed matter, where you sort of reduce your the space of your ground states to conjugacy classes. And that sort of tells you how you can decompose, for example, 3D phases into direct sums of 2D phases. And if this analogy sort of holds, right, then what we can actually look at from just Wen's perspective, what we can look at is the fusion between, for example, if you have Z4 magnetic gauge fields and Z2 electric gauge field, we can look at the fusion between these two excitations, and they have, for example, codimension 1, codimension 2. I'm just wondering if you've ever like, is there a analogous picture that you can have in what you're doing?
I think we should probably have a longer discussion later because I don't understand condensed matter physics nearly well enough to be certain that I'm familiar with what you're referring to. Certainly in the dimensional reductions I'm familiar with, there is some ambiguity about how exactly to go, for example, from a three-dimensional theory to a two-dimensional theory. There is a lovely paper written a few years ago by Over Harani, Brian Willett, and one other individual whose name I'm forgetting, who looked at this sort of issue. And they argued that depending upon how exactly you take the limit, you can indeed get two-dimensional theories, which are disjoint unions, sums of two-dimensional theories. From a given three-dimensional theory. That sounds like it's what you're describing, but again, I'm not expert at condensed matter physics, so I don't want to swear that that's the same thing. But in any event, let's definitely chat later. If not in a breakout room, then in some other context, I'll be happy to, drop me a line. I'm happy to chat.
Okay, sounds good. Thank you.
So thank you for all the questions, and thank you, Eric, for the very nice talk. And we just have time now to introduce the next speaker, who's going to be Tudor Dimoft from UC Davis in Edinburgh. Can you? Hi. Okay, can see you, and can you share your slides?
Let me try to do that.
So, and he'll be talking about 3D mirror symmetry and home-fly homology.
Yep.
So we still have maybe 2-3 minutes, so but perhaps it's better just in case someone is actually coming for your talk. So let's just wait a moment. So you can, I think that it should be fine. You should be able to move the slides and everything. So I guess then, after all, we had time for yet one more question. Sometimes it takes a bit longer to set up.
Yeah, teaching a 10-week course this past spring on Zoom sort of makes things run much more smoothly.
Yeah, everything is all set up to already. Yeah, was it like that the first time?
No. There is a lot of trial and error.
Yeah, we just have just less than a minute, and I'll introduce you again if you don't mind.
Yeah, that sounds great.
Just one comment is that if anyone is interested, there's a discussion of the talks going on in the chats. So if you look at your chat, probably you'll see discussions from the previous talks.
And how are the breakout sessions working afterwards, or will you explain that?
I think that Jeff will explain that just after your talk. Exactly. So you will be asked which session you would want to go, and then you manually send there. Okay, so it's about time. So we're very happy to have Tudor Dimoft from Edinburgh and UC Davis talking about 3D mirror symmetry and home-fly homology.
Thank you so much. And thank you for organizing this online despite everything. So I'm going to talk about some work that's sort of been ongoing for embarrassingly 2 years or so with my student Nick Garner, Justin Hilburn, Alexei Oblonkov, and Lev Rozansky. it's sort of related to a wider circle of ideas involving how 3D mirror symmetry acts on extended operators of various kinds, or maybe from a more mathematical standpoint, establishing some homological version of 3D mirror symmetry involving categories and higher categories. The talk I'm going to give today is what I think of as a fun application of a lot of these ideas, and it's teaching us also a lot about what homological 3D mirror symmetry should look like. To paint an overview of the talk, one classic starting point when discussing knot homology in relation to physics involves classic conifold setup of Oguri-Waffe that then Gukow, Schwarz, and Waffe related to knot homology, and Dunfield, Gukow, and Rasmussen proposed the existence of a triply graded homology theory categorifying the Homsley polynomial involving counting M2 branes in the resolved conifold that end on a Lagrangian labeled by a Nader link. And so in the talk today, I'm actually going to take this as my first starting point, and then try to motivate how in a particular case of a so-called tight braid, when the knot or link in question is expressed as a braid that in the limit that the braid stands are very, very close together, and it sort of looks like many, many copies of the unknot, twisted up just a little bit. One can compactify this conifold setup, and the M2s become D2s, and we can look at the world volume theory on these D2s, which is going to be a 3D n=4 gauge theory. And what one ends up with is precisely the setup that Oblomkov and Rozansky have used the past few years in what I'll call the B-twist of this 3D n=4 theory, to give a new formulation of Homsley PT homology. And their work is based in algebraic geometry and has to do with matrix factorizations, and I will say a little bit about that, but my focus will be more on like what sort of physical setup leads to this mathematical calculation. I should also say that an important motivation in the work of Oblomkov and Rozansky also came from looking at Gukow-Witten surface operators and work that Gukow and Witten done about braiding on surface operators. And so one can get to this 3D n=4 picture also by a reduction of 40 angles with a surface operator. That is another way to get to the same thing. And then hopefully I'll get a chance to talk about the new stuff, which is applying 3D mirror symmetry to this whole construction. We're applying 3D mirror symmetry not just to the bulk theory, which ends up being a theory whose Higgs and Coulomb branches, well, it's the ADHM quiver theory in the bulk. Its Higgs and Coulomb branches are both copies of the Hilbert scheme. Applying 3D mirror symmetry to that bulk theory is easy and well known, but then we need to apply it to a boundary condition and a certain line operator sitting in the middle. There are many ingredients in this setup. And we can do all that and then ask a question again about what the Hilbert space on a certain solid cylinder is. That's how this knot homology appears. the calculation looks very different. The B twist has become an A-type twist. And a nice surprise in the end was that at least for a certain family of so-called algebraic knots, what we get actually reproduces a conjectural computation of the Humphrey by Gorski, Oblomkov, Rasmussen, and Schende involving affine Springer fibers. And so there's a really nice connection to that. Yes, and as I said, many of the tools for understanding this 3D mirror map have come from some recent work of myself and others. Especially like the recent things especially involve understanding what's happening on the A side. Okay, so let me start with a very brief review of the conifold setup and start compactifying from there. So the resolved conifold can be thought of as a Kähler quotient of C4 with a U1 action that has weight 1 on 2 complex coordinates and weight -1 on the other 2. Algebraically, that's equivalent to a C star quotient of C4 with the locus where the first 2 coordinates, x1, x2, are 0 is removed. And so the details here are not super important. The resolved conifold is a C2 bundle over P1. And the story I'm going to develop sort of all happens in a neighborhood of the north pole of this P1, where locally we can just think of this as C3. And so there's a U direction. Well, the direction I'm calling U is very close to the North Pole along the CP1. And then there are fiber directions W and Z. The compactification I'm going to try to do involves a U1 action that rotates these coordinates I called x1 and y1 in opposite directions. So what it does is rotate the CP1, and it rotates one of the fibers above the North Pole. And after we transport that rotation to the South Pole, it ends up acting on the other fiber. But one of the copies of C at the North Pole is invariant, and one of the copies of C at the South Pole is invariant. So the Z direction isn't being touched here. Right, so if we did simply that compactification in the neighborhood of the North Pole, this U1 action I'm using has a fixed point, and that leads to a D6 brane in type 2A theory. Now, just the bulk geometry is not enough to get knot homology. The geometry of an otter link is encoded in a Lagrangian in the resolved conifold. And in M theory, one wraps M5 branes on this Lagrangian. The construction of this Lagrangian involves starting with the deformed conifold T star S3, where it's the conormal bundle of the knot. And Witten showed a long time ago that, well, in this case, things are related to Chern-Simons theory, and then Aguirre-Waffa described these Lagrangians. Anyway, after going through a Gopa-Kumar-Waffa large N transition, this conormal bundle of the knot becomes some Lagrangian in the resolved conifold that's been described in greater and greater levels of detail and generality. The construction we actually used when we're trying to be careful about this appeared in a paper of Diaconescu, Schende, and Waffa some years ago. The topology of this Lagrangian, for what it's worth, is S1 times R2. And the things that give you knot homology are M2 branes. So in knot homology, one is looking at BPS states of M2 holomorphic disks that end on the S1 in this knot Lagrangian. That is most of the story. However, for triply graded homology for Humphrey, one needs an additional grading, an A degree. And did I write that in? I didn't quite write that in. I'll talk about that in a second. I wanted to say a bit more about the M2 disks first. So before getting to A degree, this Diaconescu-Shinde-Waffe construction is especially nice in the case of what are called algebraic knots. And I'll revisit algebraic knots at the end of the talk because they're also especially nice in the A side field theory construction. So an algebraic knot is a knot that comes about as the intersection between an S3 inside C2 and a plane curve, typically a plane curve singularity, written as the solutions of some polynomial equation P of W and Z equals 0. And so, for example, if you want to describe the unknot this way, there are several different ways to do it. You can just take the equation W equals 0 and intersect that with S3. And I wrote Aganagic Waffe next to that because there's Aganagic and Waffe wrote down a family of sort of famous family of toric Lagrangians in the resolved conifold, and it's one of those Lagrangians that are relevant for this case. But there are several other ways of representing the unknot. And if you want the trefoil, you can take the polynomial W squared minus Z cubed, for example. But there are multiple ways of representing any knot like this, any algebraic knot like this. The really nice thing about the Diaconescu-Shinde-Waffe construction is that the Lagrangians LK they write down are precisely such that the M2 holomorphic disks related to an algebraic knot wrap these curves P equals 0. The Lagrangians themselves are actually horrendous to write down explicitly, but the M2 branes are really nice, and so they just wrap these singular curves in the C2 fiber above the North Pole in the resolved conifold. Okay, and then I'll say the final thing about A degree. So to get higher A degrees in Humphrey homology, which splits by A degree, there's an additional thing one can do, which is to add extra M2 branes wrapping the compact P1. And so if you want the A to the K part, if you want to categorify the A to the K part of the Humphrey polynomial, you add K extra M2 branes wrapping that compact P1. So so that's the geometry with all the bells and whistles. And now we can ask what happens if we do that circle compactification that I discussed before. Assuming that the knot is sort of the form I described, where it's approximately the unknot sort of wound around itself many times with a bit of braiding, then our M2 disks are also going to be multiply wrapped disks. So if I express this as a braid on n strands, then I have an M2 disk that is wrapped n times. And after the compactification, this becomes n d2s. The d2s end on a stack of ns5s. So the m5s that had been wrapping the knot become ns5s. And there's a little caveat I should throw in here. If you use the Agenagich-Waffe Lagrangian, you don't actually get this. You do the compactification and you end up with d4s. But as long as you deform this Agenagich-Waffe Lagrangian just a little bit, as for example in Diaconescu-Shende-Waffe, then you get ns5s. And so you end up with locally with a really sort of familiar brain construction of a stack of d2s ending on a stack of ns5s. Everything is in the background of a d6 coming from that north pole of the P1, where which is a fixed point of the rotation. And the extra m2s that were wrapping the P1 now just become strings that sort of intersect the d2s along a line. And we can translate that entire thing to field theory. So if we focus on the world volume of what had been the M2 brains, now they're D2s. A bunch of D2s sitting inside a D6 give us the ADHM quiver. So it's just the classic construction of instanton moduli spaces. Here it's abelian instantons. So because there's a single D6, so we get a 3D n = 4 theory whose gauge group is UN, and whose matter, whose hypermultiplets sit in a quaternionic representation T star V, where V is the Lie algebra of GLN and a copy of C to the n. In other words, an adjoint and physics terms, an adjoint and a fundamental. The Higgs branch of this theory is the Hilbert scheme of endpoints on C2 once it's been resolved, and so is the Coulomb branch. And it's maybe worth pointing out that the C2 in this Hilbert scheme, in this Coulomb branch Hilbert scheme here, is literally the U and W direction in the resolved conifold. So this 3D field theory is living on disk times time, and it's got an interesting boundary condition. That's again a familiar boundary condition. It looks just like a reduction of the T of G type boundary conditions for the Yang-Mills that Kyoto and Witten wrote about. In sigma model terms, I can describe the boundary condition as coupling the bulk theory to a copy of a T star flag sigma model. Flag is the flag manifold for GLN. And the coupling involves a certain superpotential that combines one of the adjoint fields of the bulk theory and the complex moment map for the UN action on the flag manifold. Perhaps the most important thing to say about this boundary condition is how it actually encodes this braid. So the braid was coming from the Lagrangian and the conifold, which turns into positions of these NS5 brains after we compactify, which turns into, and these positions become a bunch of complex Fi parameters. They are two-dimensional Fi parameters on the boundary, and they're literally resolution parameters of this flag manifold that's appearing. And each of these complex Fi parameters is telling you the location of a certain strand of this braid. And as we go around the boundary, the Fi parameters can move, and this motion encodes the actual braid that we have. So finally, there are the extra M2 branes on the P1, and they compactify to a fundamental string, and they give rise to a Wilson line operator. And it's a Wilson line. In the gauge theory, it's in the kth exterior power of the fundamental representation, or if you want to think of it as sort of on the Higgs branch, that ends up describing a certain bundle on the Higgs branch, which is just the kth exterior power of the tautological bundle of the Hilbert scheme. So, so those are sort of the three ingredients in the field theory. And then knot homology is supposed to come about as the BPS Hilbert space of this theory. But we can't just say BPS because there are a lot of different BPS things in 3D n equals 4. We have to be a little bit more precise about what sort of BPS states we actually want to look at. And the answer, going more carefully through this, is that it's the Hilbert space in the 3D topological B-twist. And at this point, I need to have a little digression into topological field theory in 3 dimensions. So first, all 3D n equals 4 gauge theories admit 2 topological twists. And sigma models admit these twists, but with certain constraints that are beyond the scope of the present talk. So I don't think they were historically called A and B. Quite a few of us are calling them A and B now. The reason I call them A and B is because they're directly analogous to A and B twists in 2 dimensions. They're in fact directly related to A and B twists in 2 dimensions upon further compactification. And they are exchanged by 3D mirror symmetry, just like 2D mirror symmetry exchanges A and B twists in 2 dimensions. To orient folks a little bit, the A twist is a reduction of the 4D Donaldson-Witten twist. Various aspects of it have been studied over the years. It was some versions of the A twist and sigma models were described by Kapustin and Bias. Telemann described aspects of the relation between 2D mirror symmetry and 3D mirror symmetry involving in a significant way this 3D A twist. And this was important in recent work of Braverman, Finkelberg, Nakajima on colon branches, and the more recent things collaborators and colleagues and I have been doing involve describing categories of line operators in the A twist. The B twist was first observed to exist by Blau and Thompson, and it played a major role in work of Rosansky and Witten. This is the B twist of sigma models. And Kapustin and Rosansky and Salina described higher categorical structures in the B twist. In gauge theories, there are surprisingly intricate features that appear that are being studied with cutting-edge derived algebraic geometry nowadays. This is work of Hilburn and Yu and Hilburn and Sam Raskin that's ongoing right now. I won't need any of that for this particular application. So second part of the aside, so first there are these A and B twists in 3 dimensions. Some things about them are understood, a lot is not, especially at categorical levels. So second part of the aside is just roughly what one expects from any 3D extended TQFT. There are 2 ingredients that are important for the current application. One is the category of line operators in the bulk. And one is the 2 category of boundary conditions and line operators on that. So in the bulk, line operators form a braided tensor category, just like they do in Chern-Simons theory, except it's going to be some DG version of a braided tensor category in this case. Boundary conditions should form a 2 category, and the aspect of that that's quite important here is, given a fixed boundary condition, one can consider line operators sort of bound to the boundary, self-interfaces of that boundary condition. And these line operators bound to the boundary, called endomorphisms of that boundary condition's little b, form a tensor category. And it's a tensor category just because these self-interfaces can be collided with each other. And that's the tensor product. There are 2 operations that relate, line operators in the bulk and line operators on the boundary. Given a bulk line operator, one can bring it to any boundary condition. There's a bulk boundary map. And yeah, it's just sort of written mathematically what that is. So that's a functor from the bulk category to, in fact, the center of this monoidal category of endomorphisms on the boundary. And there's a map the other way, which says, given any boundary condition, wrap it on a cylinder. So consider a theory that has sort of a solid cylinder drilled out with your favorite boundary condition on it. And you can enhance that by using a self-interface, which I called beta in this picture. And if you zoom out, then from far away, this looks again just like a line operator. And so this wrapping on a circle is a way to take a boundary condition with interfaces and turn it into a line operator. Okay, so that's the end of the aside. These operations and these categories end up being relevant for computations in the A-twist and the B-twist. In this work of Oblomkov and Rosansky, which I should say is also closely related to work of Gorski, Negutz, and Rasmussen, involving Zorgel bimodules. Anyway, in Oblomkov and Rosansky, one has a 3D n equals 4 theory, gauge group UN, representation, adjoint plus fundamental. Higgs branch is the Hilbert scheme. The category of bulk lines is, in the full gauge theory, is some horrible thing, but if we turn on a real Fi parameter and resolve the Higgs branch, it just maps down to coherent sheaves on the resolved Higgs branch, which is the Hilbert scheme of endpoints on C2. Then I said before that that line operator we had stuck in had to do with exterior powers of the tautological bundle. Now I literally mean that as a coherent sheaf. So as an object in the category of bulk lines, that line operator in the middle is the kth exterior power of the tautological bundle. And then Oblomkov-Rosansky very carefully identified what the monoidal category of lines stuck to the boundary was, and gave it a description in terms of some matrix factorization category where the tensor product comes from convolution. And again, the details here are extremely interesting and not important for this talk. The important point is that there is a representation of the braid group inside this category of line operators on the boundary, which literally comes from the fact that physically you have these complex Fi parameters and you can just move them around each other. Moving them around each other very quickly creates a line operator or a self-interface on the boundary, and that self-interface is an object of this category. And so the braid group gets represented. in the category of lines on the boundary, then you apply the compactify and S1 map to turn a boundary condition with a bunch of braiding interfaces into a coherent sheaf on the Hilbert scheme. You turn it into a bulk line operator, and then just compute derived Hom between this bulk, derived Hom between this bulk line operator and the thing that was counting a degree and the exterior power of the tautological bundle. Let me just give a picture of what that looks like in physics. So we're trying to find the Hilbert space of a theory in a solid cylinder. It's got a line operator in the middle, and it's got a boundary condition with a bunch of line operators on it on the outside. We can use a state operator correspondence. We invert, we sort of peel the boundary of the solid cylinder away and down, invert this entire picture, turn the boundary into another line operator. And that's this Chern character map, the compactify and S1. So now we have sort of a very, very thick line operator coming from this wrap boundary condition with a braid interface. And we have our very simple Wilson line, LK. And the Hilbert space on the left has become local operators at the junction of this Wilson line and this very thick boundary condition. And computing local operators at a junction of two lines is what derived Hom or Ext in the category of coherent sheaves does for us. So this is at least one way to get the answer, and is one way that was just made very explicit in the mathematical work. Great. So, so now let me go through a few pieces of the 3D mirror construction. I may even finish before time is up because I've been going too fast, fearing that I would run out of time. So the mirror of the bulk theory is itself. This is very famously self-mirror. A case of this was described in the original work by Interligator and Seiberg. And in terms of brain constructions, this was in work of De Boer, Horioguri Ozanian from the mid-90s. The thing that's changed in the mirror is that the Higgs and Coulomb branches have swapped. In particular, now the Higgs branch, which is sort of parameterized by eigenvalues of the adjoint X and Y fields, corresponds to the U and W directions literally in that resolved conifold picture we had at the beginning of the talk. The boundary condition can also be analyzed through a local brain construction. And unsurprisingly, to anyone who's learned about S-duality of boundary conditions in 4V knows, the mirror of that seemingly complicated T-star flag boundary condition is pure Dirichlet. It's a boundary condition that simply breaks the gauge group at the boundary and fixes half of the hypermultiplet fields. And here it's fixing X and, well, one of the adjoints and one of the fundamentals. The complex Fi parameters that were resolutions of this flag manifold have now just become fixed eigenvalues of the adjoint field X at the boundary. So this is just phenomenally simpler than what was happening on the other side. And the braid, again, comes from taking this local boundary condition and changing it as we go around the circle. And so we'll just braid eigenvalues of our X field. There is also this, this line operator going through the center of the cylinder. And to say what it is, I need to say things in categorical terms. And so I should tell you a bit about the category of bulk line operators in the A-twist, which, the way I've written it here, looks maybe horrendous. Physically, what you would want to say is that this looks like some sort of Fukaya category on the loop space of the Higgs branch. And here I've given you a mathematical description of it that seems to be leading to sensible calculations. So this is an algebraic description where we take the algebraic loop space of not quite the Higgs branch. One needs to remember that this is really a gauge theory. And so it's, the way I've written it is in stacky language, and I think the details are just not sufficiently important right now. But this is a thing that makes sense mathematically. Or you can think of it as strongly equivariant D modules so equivariant for the loop group on the loop space of the matter representation. And because we've gone from something Fukaya-like on the entire Higgs branch to D modules, we should be just looking at sort of the base of the cotangent bundle, and so this is why I only have half of the representation there. It's only half of the hypermultiplet fields that are around. Look briefly at the audience. I think there are probably more physicists out there than mathematicians, so let me also just say physically what's happening. So in the line operators in the A-twist are vortex lines, and they're typically disorder operators, and they're described by giving a holomorphic singularity to fields in the plane transverse to a line. And objects in this fancy category involving a loop space can precisely encode either poles or zeros in various hypermultiplet fields as we get close to the line. And I am going to run out of time. Anyway, the mirror of the Wilson line can be analyzed using brain constructions that were described by Asel and Gomis, and then we explained with Garner, Gerasi, and Hilburn how to translate that to an object of this fancy D module category. I'm just going to say right now that it can be done, and roughly what it does is to give a 0 to k rows of the x field and to give a pole to k columns of the y field as one gets close to the line operator. And then there's, so I think I've actually described everything. And then what's left to do is a computation of this Hilbert space on the solid cylinder. And the computation is really beautiful in the special case of what are called positive algebraic knots. The algebraic condition is just so that we end up with an algebraic object in this category of D modules that's described algebraically. Otherwise, one has to do more work. The positive condition is a technical thing, and it has to do with not going to have time to talk about it now. But what is one of these things? Yeah, I should finish up. I'll just say this very quickly. So when one takes a knot described by say a plane curve singularity, expresses that plane curve singularity as the characteristic polynomial of some matrix, and then that matrix is literally going to encode for us the boundary condition. You take this variable z restricted to the unit circle, and now you've got you've got what your X field is fixed to all the way around this solid cylinder. And then there's a calculation. Apply this categorical Chern character map, get down to the category of D modules. And at the end of the day, you're computing a hum of D modules, which ends up being homology of a certain moduli space. That's an extremely concrete mathematical thing. Also, physically, this is counting vortices. So the Hilbert space in the A-twist of this 3D n equals 4 theory is the cohomology, is the de Rham cohomology of vortex configurations, of the moduli space of vortex configurations on this disk, with a certain singularity at the origin and a certain boundary condition along the outside. This is just a way of making that mathematical. And I will say the final thing, which is that this is a conjecture for Humphrey homology, but it is in fact provably related to another known description of Humphrey homology. And so my student Nick Garner and Eugene Gorski's former student Astrid Kuvinen actually wrote a paper, and they're writing another one, proving that this moduli space that shows up in this computation is the same one as that appeared in work quite a few years ago by Gorski, Oblomkov, Rasmussen, and Chende involving affine Springer fibers. I'll take 10 seconds to conclude. So there should be, this isn't far from the end of the story. For non-algebraic knots, one needs to actually figure out a braid representation in some A analog of the matrix factorization category that Oblomkov and Rozansky had. This is interesting and very much in progress. It looks like there is some Fukaya-Seidel category involved. And let me just come back to an initial motivation for all of this. So in many ways, for me, this is a fun application of a broader set of ideas and these examples relating to not homology, which are things things one knows, or at least concrete things to connect to, are really teaching us important lessons for how 3D mirror symmetry should act on things like two categories of boundary conditions, which I think is interesting and very much open still. Thanks.
Thank you. If someone can unmute people, because I don't seem to find out still how it is. I guess not so. Yeah, so then thank you. And then now we can mute all.
Oh no, sorry, Ines, you've been muted yourself.
I unmuted you and I forgot to unmute myself. Yes, so we already have one question by, sorry, I can't say your last name, Aswin.
Hey, yes.
Yeah, that's okay. Yeah, hi. Hi, Tudor. I had a question. So what is the compatibility condition between the choice of the Gukov-Witten surface operator and the 3D n equal to 4 theory? Should the corresponding T-star flag manifold be related to the Higgs or Coulomb branches in any way? Or
yeah, and of course there are lots of dualities there. So it depends what side you're working on. But yeah, so so you can start in 4 dimensions with, sorry, the compactification we're doing, let me just say that, is a circle compactification in the plane transverse to the surface operator. So locally, we have a surface operator in 4D, and transverse to it is a plane where the surface operator is at the center. And then we're doing a circle compactification on a circle that is contractible. So locally, when we do that, we will end up with a 3D theory on a half space, on a 3D theory where the surface operator from 4D has become the boundary. And there's a way to globalize this. And if you want knot homology from a Gukov-Witten scenario, then you have to put your surface operator on a circle, and it's all sitting inside a 3-sphere. And then you do this compactification, and you end up with the solid cylinder in 3D. That's describing the geometry. Otherwise, it's the same sort of thing. So Gukov and Witten precisely coupled to like T-star flag to describe their surface operators in n equals 4.
But then is T-star flag some kind of subspace of either the Coulomb or Higgs branches? Is that the way to
no,
check the
it's
boundary
not.
condition? No, it's not. Okay.
No, it's not. In general, on a boundary condition, you can introduce any two-dimensional theory whatsoever.
Okay.
That has the right supersymmetry. And then you couple it to the bulk by introducing things like superpotentials or gauging part of the boundary the boundary flavor symmetry with bulk gauge symmetry.
Okay.
So yeah, it's not. You should think of this as a higher dimensional analog of a Chan-Paton bundle. If you have a boundary condition for a two-dimensional theory, you can tensor it with a vector space. That's the Chan-Paton bundle.
Okay.
And so here we're tensoring things with T-star flag.
Okay. Thank you.
Yeah.
Thank you. So we have another question from Sergei Gukov. Can you unmute yourself?
Yes, I think I can.
Yes.
Hi, Tudor. Thank you for a very nice talk. This was quite a story. I have a very lowbrow question, as Nadia would put it. Suppose we change framing of a knot by 1 unit. So how does homology change, and how do we see this in the physics of line operators that you described?
It's not in the line operators. It's going to be in the boundary condition, and I am honestly not sure. I think for the A-side calculations that worked out, there must be some canonical choice of framing on these algebraic knots. Otherwise, it had better be part of what you would expect is to find a line operator on the boundary that changes framing on a strand. And so in the matrix factorization category that Levin elects use, they must have something like that. And I don't know. But it as you point out, it has to be there since these are invariants of framed knots. And it had better appear in this sort of Fukaya-Seidel category that has a braid group representation on the A side as well. But yeah, that is, I don't think that's a lowbrow question. That's an interesting thing that we need to figure out.
Okay. Thank you. I think we have one other question from Mina Ganajic. If you want to unmute yourself.
Okay, yeah, I managed to do it. Thank you, Tudor, for a wonderful talk and a wonderful story. I have one question about the comment that you made about the relation, whether the boundary condition is an NS5 or a D4 brane boundary condition.
Yeah.
Within the Calabi-Yau threefold, I don't think there's any room for this kind of deformation. Simply because the M5 brane is occupying simply all the circle symmetries. So could it be that what you're doing is somehow pushing the M5 range very, very far at infinity, where at infinity, you don't really have a Calabi-Yau threefold, you have a smaller structure. In other words, it's almost like a twofold times C star. And that's where the whole story happens at infinity, so your M5 rings can never ever be, you can never push them close to the confold. They're always far at infinity. Where at infinity, they can be essentially holomorphic.
That may be a useful thing to do regardless. I think it's easier. So in general, one of these Lagrangians associated to an algebraic knot, if the equation P of ZW equals 0 has a symmetry, and often it does, then the Lagrangian can also be engineered to have that symmetry, but that's almost never the U1 that I'm using to compactify. And so unless you are silly about it and use the wrong version of the unknot. So the one case where they do coincide is for the simplest version of the unknot, W equals 0. But if you use W equals Z instead, then the symmetry that preserves that is not the U1 symmetry.
So which U1 symmetry are you using?
So
I think we've used up all of them.
I did not. So there's because. Okay. So I'm using a U1 symmetry that leaves one of the copies of C above the North Pole alone entirely, and it rotates the other copy. And so this is a specific choice. And these Lagrangians are often invariant under a U1, but it's a different U1. And so upon this other U1 symmetry just rotates them around, and it doesn't leave them invariant. And so I think in general one does get on S5s.
Could you just briefly repeat again which U1 symmetry is that? Because
sorry,
if you say it one more time, maybe I would.
So it's a U1 that rotates the P1, and it rotates one of the fibers above the North Pole, but not the other one. In particular, the fiber it doesn't rotate is the same as the Z that shows up in vortex counting on the M2 brains. I think the relevant thing is that there's just one copy of C that is preserved pointwise.
There's something that bothers me about this, but okay, fine. I don't think I can complain in real time. So go. I'm sure your story is correct. So the only question is perhaps how it is correct. But
I'm quite happy to discuss this in more detail and make sure that everything fits. Yeah.
So thank you. So there's one last question before we go into the breakaway rooms. We're basically out of time in any case. So, well, I would like to thank both the speakers, both Eric and Tudor. Thank you for the very nice talks. And I think there'll be now time for actual long discussions.
Thanks, Ines. Thanks, everyone.
And so I don't know how it's going to be now. Is everyone going to be split?
Ines, I'll
yes,
thank you very much. Very good. Thank you, Ines, for chairing the session, and thank you to the speakers of the session. I have requested in the chat for anyone who has a preference for which session to join. I'm going to give it a few more minutes and then open the room at rooms at 7 p.m. That's in 5 minutes my time. The rooms will remain open for an hour. We'll start, and if the discussions go on further than that, then tomorrow we'll extend it, etc. But for today, I'm going to start off by opening them for an hour. I have broken the rooms up into 2 rooms for session 1, which were the first 3 talks, and session 2, which were these last 2 talks. And the speakers for the sessions were automatically assigned to those rooms. And I have requested in the chat, if anyone wants to move into any particular room, please send me a private message. And the only content that needs to be there is session 1 or session 2. And I will move you in there, and then I will open the rooms. If there's no preference indicated, I will leave you in the main room, and you can always ask me a little later where to move you. You can also move between rooms should you want to. Again, just send me a message. So let me ask again, if you have any preference, to please send a private message to me in the chat room. If you're a speaker, you don't need to, for today's sessions, you don't need to tell me, you will automatically put into your session. So in 5 minutes, I will open up the sessions and you will get an invitation to go to a particular room. Thank you.